of spintronics. One moment. And permanent increase of magnetic recording density or number of switching elements in the microchips requires a new method of their function due to increased technological limitation. So spintronic manipulate with electron charge, not only with electron charge as conventional electronics, but also with its spin. Please, next slide. And next, please. Here you can see some example on spin electronic devices. These devices are very wide use in various branches of electronics. And let's go. Let's go. The next. And the problem of remagnetization, this is the main problem of our work. The remagnetization of the small nano-size element is the big problem because of complexity, because of difficulties to create the small elements of coils, and it is difficult to remagnetize with the high speed so small volumes. Moreover, the small volumes have the scattering fields, and it is very difficult to remain the magnetic state and change it under the special external influence. So we use some method for remagnetization to help to usual remagnetization by magnetic field. Please, the next slide. These methods are spin polarized current using optical radiation, electric field, and even mechanical strain based on magnetoelastic effect. Straintronics, so-called magnetoelastic branch, is taking a special place among them. It operates with mechanical deformation of the spin cell, making it possible to magnetize the unit cell with smaller magnetic field. Even without applying external magnetic field, I will then speak about this. The next, please. Composite structure have some advantage over monofilm due to combination of several substantial properties that makes it possible to remagnetize them not only by conventional external magnetic field, but also by applying mechanical stress. Our previous study of mechanical stress ferromagnetics of various compositions show a possibility of changing shape of their hysteresis loops. Then I shall show this in on the diagrams. And please, the next slide. Experimental methods mainly based on magnetooptics, but not only. We have some facilities with ferromagnetic resonance and some other electric facilities, but magnetooptics give us the possibility to observe the domain structure, diffraction of this domain structure, and also to record the hysteresis loop of our samples that consist of ferromagnetic and piezoelectric connected with one another. Next, please. The next slide, please. No. Следующий, пожалуйста, переключите. Не идет?
Я переключил.
Ну да, а у меня нет. Now. Here is the some results obtained with Magnetoelectric. You can see the domain structures of ferrite garnet and diffraction on it, and also in the down right. Отключилась почему-то совсем. Давайте, может, я включу хотя бы вот таким вот образом. Well, the next, please. The next slide, please. Besides the experimental results, we also calculate the remagnetization, and here is shown some components of magnetization energy model that were taken into consideration in order to obtain the results. The results magnetization and hysteresis loop. Please, the next. The next slide, please. Не переключается это. Да? No. Может, давайте я переключу на свою, пусть не на полный экран, но хотя бы буду переключать, перемикати її там вчасно. Добре? Давайте спробую так поки що зробити. Ну, тут, мені здається, в принципі, видно. Ось компоненти of components and diagram of various type of energy that were taken into consideration, and we have obtained some spatial diagrams that have a minimum in which the magnetization vector is situated, and successfully reading these coordinates of this minimum, we can obtain the calculated hysteresis loops in various conditions of directed magnetic field and in various for various parameters. Next slides show the hysteresis loop obtained experimentally, and you can see that it can change from almost linear to almost sometimes rectangular, sometimes with one jump. So the shape of hysteresis loop can be various depending on the mechanical stress that we apply to this material. But one of the problem is remagnetization with high frequency, and antiferromagnets have a significant advantage in remagnetization rate of any other magnetooptical materials because of some non-collinearity of their magnetization of the sublattice. So the resultant processes of their magnetic moments lead to fast changing of spatial orientation of magnetization. And studies of domain wall that is showed here on the photo give the information about the process that take place in such materials. And here you can see the hysteresis loop of such orthoferrites that can be remagnetized very quickly on high frequencies on 100 megahertz, and the speed of moving of the domain wall moving is up to 20 kilometers per second. This is much more than 4 kilometers per second of sound in this material. So only with these materials we can remagnetize quickly with the high frequency. So the next stage of investigation was using of sandwich structures of piezoelectric. It was PZT, plumbum zirconium titan, or PMN PT, plumbum magnium niobium, plumbum, and titanum. It's very famous piezoelectric, and in contact with ferromagnetics that can be remagnetized and studied one moment, two types of magnetoelectric effect, because they very high in such a sandwich structure and usually divided on direct.
Dear professor, sorry, but your time is out. Okay, thank you.
So I'm finishing. Here are some results on magnetoelectric effects in orthoferrites. I have no time to show this in details, to my regret. But maybe if the presentation will be on the website, we will show this. Concerning some conclusions, we have noted that modeling
Thank you very much for your very interesting presentation. We have limited time and can't listen all your speech.
Yes.
And please, who have questions, please? The questions. Nobody. Okay, I have two short questions. Tell me, please, is it possible to apply in supertronics superparamagnetic materials? And how about a hematite structure that, as it is antiferromagnetic modification of iron oxides? Is it possible to apply it for devices that you speak about that?
And we also try to explore some of such materials, but such investigation we provide in another group.
Okay, thank you.
And it's material for another. Need a very long time for explanation. Thank you.
Okay, thank you very much. Okay, our next speaker, Professor Alexander Rud. from Kurdumov Institute for Metal Physics, NAS of Ukraine. Are you here? Professor Alexander?
Yes, yes, yes.
Okay.
I am.
Please, we're ready
Do
to
you see
listen.
my presentation?
Not yet. Yes, now we can see it.
Yes, now I can see it. Это не у нас.
So, Professor Root, we can start.
Где наш профессор?
Hello, are you hearing me?
Oh, yes.
Yes, now we can hear you, but we no longer see your presentation.
One moment, please. I see Victor Kisluk at my monitor. Victor, turn off, please, your ecran.
Okay, but it's only my.
Turn off, turn off.
So now Victor Kisluk disappear, and you can share your screen, please.
Do you see my presentation?
So now,
Please use control monitor.
now we will try to open your presentation on our laptop.
Yes, please.
Please, you can start.
Yes, thank you. Good morning, dear colleagues. My presentation is devoted to study a very interesting class of carbon materials called carbon nanospheres. The second one, please. The second slide. The second slide, please. Thanks. The most known representative of the carbon nanosphere are onion-like carbon or onions. Carbon forms more compounds than other elements. For now, it is known more than 10 million compounds with carbon. So the classification scheme of carbon materials is a very important task for science and technique. We use in our work a scheme proposed by Hyman, Yevsikov, and Koha, where all carbon materials are placed on a triple quasi-diagram of states with main representatives in cones, namely graphite, diamond, and carbide. They main carbon allotropes have differ by type of sp hybridization of valence electrons in carbon atoms. You see that the center of triangle is occupied by a very big class of carbon materials called amorphous carbon, including onion-like carbon. The next one, please. Next slide, please. Onion-like carbons was discovered in 1980 by Ijima before discovered fullerenes, and only after in 1994 was developed technology for large-scale production of carbon onions based on vacuum annealing of nanodiamonds. Next slide, please. During last 30 years, a lot of technologies were developed for production carbon onions. The most known are electric arc processes of graphite electrodes, laser evaporation and electron beam evaporation of graphite, pyrolysis of hydrocarbons, detonation and annealing of nanodiamonds, and we propose to use and elaborated the new method for synthesis named electrical discharge treatment of liquid and gaseous hydrocarbons. Next one, please. Next. The method named electric breakdown of organics media and gaseous hydrocarbons is based on a high voltage or high frequency discharge between current generation into a discharge gap in hydrocarbon medium with pulse repetition about 10 up to 10 hertz, or in case of high voltage technology, or 10-20 kilohertz in case of high frequency technology. In the process of such treatment, the destruction of hydrocarbons molecules and the synthesis of carbon nanomaterials occur. We use organic media differ by chemical nature, namely in different aggregate states, liquid or gases, and differ by sp hybridization of carbon in molecules. For example, acetylene sp hybridization, benzene sp2 hybridization, and cyclohexane and propan-butan mixed sp3 hybridization. The more detailed information about synthesis technique and structure materials is presented by poster of Evgeny Polumpin with co-author at our conference. Next slide, please. The synthesized material were subjected extensive investigation, and the high-resolution electron microscopy show the presence of spherical nanoparticles, but having differ by inner structure. In case of, for example, cyclohexane, we have nanoparticles, spherical form, spherical shape, with structure type of core shell. In other cases, we have nanoparticles, spherical shape, but without graphitical layers. Next slide, please. We use Raman spectroscopy, XRD diffraction analysis, and at this slide you see the typical Raman spectra for synthesized carbon materials with the bands. But in case of cyclohexane, there are additional bands near with main bands proper to carbon materials. XRD diffraction show that all synthesized materials are in amorphous state. Next slide, please. To elucidate more detailed structure, order, atomic order, and local atomic arrangement. We used radial distribution function analysis. And next slide, please. And this is this slide show the structure factor of carbon nanomaterials produced by electric discharge treatment on liquid gaseous hydrocarbon, liquid and gaseous hydrocarbons. You see there is a difference in behavior of structure factor. As in case of benzene, in case of carbon nanospheres produced from benzene, we have typically graphite-like structure. As the place of the first maximum acidity coincide with the place of the one typical to graphite. But the next part, we see that the second peak is more intensive than the one. And it is in place typical to diamond. So synthesized materials possesses mixed graphite-like and diamond-like type of short-range order. Next slide, please. To study local atomic arranged in synthesized material, we use reverse Monte Carlo modeling. And next slide, please. Next slide. With Voronoi polyhedral analysis of carbon nanospheres. Voronoi analysis shows very interesting results. First of all, we have a lot of various type of various Voronoi polyhedra for synthesized materials. The first. The second, they have irregular shape. And the third very interesting moment, practically all of them possesses five-fold faces, typical to amorphous state. You know that five-fold faces are virtually absent in crystalline materials. And the next slide, please. And a couple of words about application of onion-like carbon. First of all, we used not only onion-like carbon as additives to oils and fuels. The second one, medicine biology application for target delivery of preparates to cells and body, additives to electrolytes, electrochemical application for supercapacitor electrodes. Carbon nanosphere can be easy functionalized and encapsulate by metals. And we used onion-like carbon as additives to magnesium-based hydrogen storage materials. And I think the field of application is very, very perspective in the future. And the second slide, please. Some conclusions. New technology for synthesis of onion-like carbon by a technique electric discharge treatment of organic liquids or gases is proposed. The structure of the proposed materials directly depends from chemical nature of working media, source of carbon. This technology enables to produce onion-like carbon in large scale at normal conditions. And finally, next slide, thank you for your attention.
Okay, thank you for your interesting presentation. And the colleagues who has the questions, please. The questions. Not questions. Okay, I have a small questions. Tell me, please, what is the main advantages, the method that you use to obtain such nanosphere?
It is a very cheap method, the first. It is, it enables to produce large scale for short time. Because synthesis from nanodiamonds is not so simple, because we should synthesize nanodiamonds.
Okay, thank you very much, thank you. And our next speaker, Любовь Patrylak from Kuchar Institute of Bioorganics Chemistry and Petrochemistry of NASA of Ukraine. Please, are you here?
Thank you very much. I'm here.
Okay. We are ready to listen your speech.
Can you see my presentation? Is my presentation visible?
Not yet. I also kindly ask all our participants in Zoom to switch off their microphone.
Can you see my presentation now?
No, we can only see yourself.
Okay. Stop share. Next. Now?
Yes, but not in a full screen.
Okay. А тепер?
No. Вам потрібно виключити трансляцію екрану, потім запустити на повний екран і потім розпочати трансляцію. Тоді її буде видно на весь екран.
Сорі, ще раз, як треба зробити?
Зараз запустіть трансляцію на весь екран, а лише потім поділіться екраном.
Хіба в мене зараз трансляція не на повний екран?
Запустіть зараз презентацію, F5 там нажміть в PowerPoint.
Демонстрація екрану у мене зараз. Запущено. I'm sorry. Може запустіть ви, щось в мене не виходить. Або я не в повноекранному режимі буду.
Там просто немає екрану, якщо зайшли з браузера, от, за тим посиланням, яке давалось. Тобто у всіх одна проблема тут.
От зараз видно мої?
Але не весь екран.
Ну, може, в такому режимі будемо, якщо більш-менш видно. Щось інакший варіант не про.
Я все время включаю это.
Can I start? In such regime.
We will start your presentation in a few seconds.
Ви перезагрузите чи мені починати з моїм режимом?
2 секунди, ми зараз запустимо вашу презентацію.
Женя, что это за звук идет?
So, you can start.
Thank you very much. Dear Chairman, Chairwoman, dear colleagues. Today, more than 80 types of natural zeolites are known. The latter, in contrast to synthetic zeolites, usually contain a number of impurities from other rocks. Next slide, please. Clinoptilolite, as a zeolite of the guilandite group, finds considerable application in various fields. It is one of the most stable and common natural zeolites in the world. Big deposits of clinoptilolite are available in Ukraine too. The shortcomings of the porous structure of the clinoptilolite, on the other hand, limits the widespread usage of this Ukrainian natural zeolite. Today, a few hours later, I hope we will listen to talk about the antioxidant properties of silver, but in our study, we concentrated on the antibacterial properties of the silver particles on the zeolite carrier. We will know utilization of silver nitrate in food packaging to prevent contamination. Next slide, please. In home appliances like refrigerators, washing machines. Next slide. As well as in several industrial applications. Argentum demonstrates antibacterial properties against gram-positive and gram-negative bacteria. However, the exact mechanism of such behavior has not been fully elucidated yet. The existing experimental evidence supports different mechanisms that consider the physical-chemical properties of Argentum nanoparticles. Such properties as size, surface, which allow them to interact or even pass through cell walls or membranes and directly affect intracellular components. Nanoparticles of silver may generate free radicals, interactive oxygen species, which lead to cell death by blocking cell replication. With the development of new knowledge in nanotechnology and relative sciences, it becomes possible to explore antibacterial properties of argentum nanoparticles deposited on the matrix too. Silver-containing sorbents based on mineral carriers, such carriers as alumina or silica systems with meso and macro porous structure, are relatively inexpensive. They can be used in gaseous or liquid media, for example, for thiophene compounds, mercury adsorption. The aim of this study was to use a complex modification of natural zeolites to obtain promising nanoscale silver-containing antibacterial sorbents. Next slide, please. Let's start from the synthesis of the samples. The raw starting material was clinoptilolite zeolite rock from Sokirnitsa village deposit in the Transcarpathian region. Clinoptilolite was initially crushed and fractioned. Medium-sized grains were used for further processing. The modification process involved dispersion of the sample, zeolite sample, in the water, adding crystals of ethylene diamine tetraacetic acid, boiling the resulting mixture for 3 hours. After that, the sample was washed. Its chemical composition was determined by X-ray fluorescence analysis, and then sample underwent further processing 4 times. The total treatment duration was 12 hours. After that, 1 weight% of silver was added to the sample by impregnating it with silver nitrate according to its moisture content. Then sample was calcined at 350 degrees for 2 hours. Significant attention now is being paid to different methods of metal component reduction. In particular, silver species are prepared using green substances like glucose, citric, oxalic acids instead of hydrazine. Gamma alumina sample with silver was prepared for comparison according to the same modification procedure. Next slide, please. The antibacterial properties of the samples were studied via total viable count, TVC, determination. We use the method of deep sowing of water in nutrient agar. All colonies, including microorganisms that grow for 24 hours and could be seen at 2-5 times magnification, were considered. Next slide, please. Sample characterization. The first stage of modification of the zeolite sample was 4-fold illumination decationation with ADTA. Both processes occur simultaneously. As is known, the advantage of using ADTA compared to another strong mineral acids is a lower degree of decationation of the samples and lower destruction of their lattice. As we can see from the first figure, the content of potassium cations decreased slightly, magnesium remains almost unchanged, while the content of calcium and iron fell significantly. This is obviously related to the removal of natural rock impurities, such impurities as calcite and magnetite. According to X-ray fluorescence data, after this Gantel process, the silica to alumina ratio changed from 7.3 to 8.7. The specific surface area calculated from low temperature nitrogen adsorption desorption isotherms increased from 10 to 80 square meters per gram. Micropore volume rise to for treated sample. Furthermore, the latter happened mostly as a result of better access to the sample micropore structure. As better micropore surface and micropore volume, all these decreased after argentum impregnation, while total pore volume remained practically constant. As we can see from adsorption data for alumina samples, they have predominantly mesoporosity and low microporosity. Next slide, please. Some images of the original rock and illuminated zeolite samples show typically crystal for natural zeolites, but images of the initial sample demonstrate some impurities on zeolite crystals, which were removed after DTA treatment, and some external surface addition we can see also after argentum impregnation on the image on the right, C image. It is interesting that in the case of zeolite sample, we show cloud-like argentum species, big agglomerates of 1-4 micrometer, and nanoparticles of 20 to 50 nanometers. Whereas on the alumina sample, image D, we show only cloud-like species that are formed in spite of similar procedure of their preparation. Thus, the nature of the carrier and its porous structure significantly affect on the form silver particles. Next slide, please. As we can see from infrared spectrum, in the region of lattice vibration, that the spectrum of the initial zeolite did not undergo significant changes after a DTA treatment, which indicates the absence of amorphization of the sample and preservation of crystalline structure. However, some shift of adsorption band of antisymmetrical Wallace vibration into the higher frequency region we can see, which the last associated with increase in the proportion of silicon in the treated sample. Thermogrammetric analysis shows that the original rock is characterized by exotherm near 100 degrees related to the dehydration process. Dehydration for original rock stops at 500 degrees, whereas for DTA treated sample, the dehydration smoothly goes to the dehydroxylation process, dehydroxylation of acid sites. The last were formed after acid treatment. Clinoptilolite zeolite, as I said above, is one of the most thermally stable natural mineral that does not show major structure changes at higher temperature, but a phase transition process indicated by exothermic effect on DTA curve is observed at temperature near 900 degrees. Next slide, please. Now, let's see antibacterial properties. The water of 3 cave lakes, Radunka, Svetoshinsky, and Sonyachne, was previously examined to determine its bacterial contamination. Water samples were taken this summer in June. According to the total viable count, Lake Radunka's water meets standard for both open water bodies and drinking water. The characteristic of Lake Svetoshinsky water are a little worse. Comparing the same information for 5 lakes in Lviv region, you can see on the slide in 2020. It is interesting that the water quality of Kyiv lakes came out to be generally not too terrible. The lake Sonячne water ended up being the worst. Therefore, this sample was selected for further study. Next picture, please. Here we have the results of a sowing of water into nutrient peptone yeast agar without zeolite on the left, and in the presence of a zeolite with silver on the right. As can be seen, the growth of colonies is significantly suppressed. In particular, there is no evidence of overgrowth. Next slide, please. Here in the table, we have results of sowing of water into agar in the presence of 0.1 and 0.2 gram of argentum zeolite and alumina samples. Using argentum zeolite leads to 60 and 200 time purification of the water samples. As a result, according to this indicator, the sample now fully meets the norms and standards for surface water and even the norms for drinking water. Then argentum alumina requires only 13 and 30 times water purification. Such peculiarities can be caused by different states of applied silver particles, which are both nanoscale and cloud-like in the case of zeolite, and only cloud-like in the case of alumina. But we cannot deny the role of argentum species interaction with zeolite matrix too. I think that this interaction can be like the interaction of Bronsted and Lewis acid sites in zeolites that promote higher zeolite acidity. Argentum nanoparticles localized near zeolite exchange cations, and that can stabilize them and additionally improve their antibacterial properties. The question of the influence of the different sizes of silver nanoparticles on zeolite matrix, on their antimicrobial properties, as well as possible silver aggregation needs further investigation. Next slide, please. According to the results, next slide, please. Conclusions. According to the results of low temperature nitrogen adsorption, the chemical modification of the transcarpathian clinoptilolite rock, VTDTA, resulted in the soft elimination of the rock, removal of the impurities, and significant improvement of its pore properties. A considerable drop in the total viable count of lake water suggests the potential of argentum zeolite application in the purification not only open water but drinking water too. In comparison with argentum aluminum, argentum containing zeolite samples demonstrate better performance in antibacterial properties. The latter can be caused by strong interaction of silver with zeolite cations. Next slide, please. We would like to thank Dr. Kamensky and Dr. Melnichuk for experimental assistance in X-ray fluorescence analysis and SEM investigation. Thank you very much for your attention.
Yes, one moment. Microphone.
Thank you for a very interesting report. I have a question. If we consider the mechanism of antimicrobial effects of silver and silver-containing compounds, it's non-specific for prokaryotic cells. I mean, its mechanism is based on the induction of oxidative stress and binding to thiol and carboxyl group of proteins, causing their inactivation. So compared to, for example, antibiotics, it's non-specific. Have you considered to evaluate the impact of your composites on eukaryotic cell, I mean on human or animal cell, to assess the toxicity, for example, of it? Because I've seen only the evaluation of the antibacterial effects, but not...
Yes, our study was concentrated only on antibacterial properties, antibacterial properties of silver particles on zeolite carrier. We don't know anything about their interaction with cells, animals or human.
Okay, thank you very much.
Who has questions? No questions.
Sorry, I have a question.
Online.
Please, question.
I have a question.
Yes, of course, you can ask.
How you confirm the presence of silver nanoparticles?
We confirm our presence of silver nanoparticles by SEM and TEM investigations.
Mm-hmm. And did you investigate the release of silver from your compound?
Sorry?
Release, stability of your compound, release of silver from your compound. Stability compounds in, for example, acidic media or basic media.
Different media. We don't have such data.
Okay, thank you. Thank you very much. No questions? Okay, that is time for our next speaker, Dr. Olga Larina from Pisarjevsky Institute of Physical Chemistry, NAS of Ukraine. Please, Olga.
Thank you.
Just a moment, we will start your presentation.
Okay.
Wait a second, we will start sharing to the Zoom.
Okay. Підкажіть, будь ласка, як користуватися?
Користуватися, дивіться, ось це
Дивіться.
переключає слайд.
Назад слайд.
Ну,
Перший.
якщо на перше, то з одного боку, з іншого.
Thank you.
Лазерная указка снизу, на всякий случай.
Process for production of valuable chemicals and fuels based on biomaterials, such as bioethanol, is an alternative to the process for production of valuable chemicals and fuels based on raw materials such as bioethanol is an alternative to a number of petrochemical processes. Bioethanol is a universal precursor for the synthesis of industrially important products such as butadiene. And this topic became of great importance after the Russian invasion against Ukraine. The zeolite and silica-based materials, acid-based materials doped with dehydrating additives, are the most promising catalyst for the process of ethanol conversion into butadiene. But now the high productivity of the catalyst can be achieved only at high load, warehouse space velocity of about 2 repressical hours, and high temperature above 673 degrees of Kelvin, and such increase in temperature provokes the increase in the formation of byproducts such as dehydration products, ethylene and diethyl ether, and regulating the acid-base properties of the catalyst is the way to change the acidic properties to decrease in strong acidic sites which are active in the acid dehydration reaction. That's why the present work in present work we studied the effect of alkali metal ions and rare earth elements on the acid base and catalytic properties of zinc, magnesium or zirconium silicon oxide systems in the process of ethanol conversion into butadiene and later ATB process. For this research, we synthesized the two-component magnesium silicon and zirconium silicon oxide systems by the wet kneading with subsequent drying and calcination. The corresponding additives such as alkali metals and rare earth element and zinc oxide as degradative additive were added by the impregnation. So, acidic properties, acid-base properties were studied by the temperature programmed desorption of the probe molecules, and as you can see that the total acidity of the both magnesium and zirconium containing samples decreases, while the total basicity, basicity increases somewhat. Moreover, we see that on the surface of magnesium-containing catalysts, the acidic sites more strong at the temperature of 590 degrees of Kelvin were formed, and the such basic properties is decreased. For the zirconium-containing samples, we also can see the decreasing in the weak and strong acidic sites. That change in acid-base properties provokes the change in catalytic activity in the ethanol conversion into butadiene. That's why for magnesium-containing catalyst, we see the decreasing in ethanol conversion, but we see the increase in butadiene selectivity. Moreover, there is some decrease in the selectivity of acetaldehyde and other condensation products. This may be due to the formation, to the decrease in the number of strong acid and basic sites. For zirconium-containing catalysts, it's somewhat another situation. The conversion of ethanol does not decrease at such level, and the selectivity to butadiene does not increase. But we see the strong decreasing in the byproduct dehydration. Byproduct dehydration reaction, and the selectivity to FN and ethyl ether decreases, but the selectivity to acetaldehyde is increased. This is caused by the blocking of acidic sites at which the site dehydration reaction occurs. It should be mentioned that the conversion of ethanol, the selectivity to butadiene, and the selectivity to butadiene and ethyl ether and FN is decreasing over the magnesium-containing catalyst with a longer operation. In turn, for zirconium-containing samples, we see that the conversion of ethanol is almost constant after the 120 minutes of operation. To study the effect of water in the initial reaction mixture, we studied the reaction with the use of aqueous and rectified ethanol. And for the magnesium-containing samples, we see that the ethanol conversion almost unchanged with the use of aqueous ethanol, and we see a slight increase in the yield of FN and ethyl ether. But for zirconium-containing samples, we see a strong impact of the water, and the conversion of ethanol decreases significantly, and we see that the selectivity to butadiene and ethane and ethyl ether also decreases, but on the acidic sides of the surface of zirconium-containing samples, the acetaldehyde formation occurs. And for about the modification of rare earth elements. The acidic properties of zirconium and magnesium containing catalysts with the modification of rare earth elements such as yttrium, thorium, and lanthanum. It's different for these two blocks of catalysts. Thus, we see the formation of weak yttrium-containing acidic sites, moderate thorium-containing, and strong lanthanum-containing sites for magnesium. Based catalyst, and for zirconium containing catalyst, there is another situation. We found that the formation of weak lanthanum-containing sites occurs, and the formation of strong therium-containing acidic sites. Moreover, I should say that on the surface of all samples, there are only loose acidic sites. The brown-state acidic sites does not found. And such change in acid-base properties promotes the change in catalytic activity. So we see that the formed acidic sites are active in the aldol condensation reaction of acetaldehyde into ketonaldehyde with successful conversion to butadiene. That's why we see the increasing in butadiene selectivity instead of decreasing in the selectivity of acetaldehyde. Over the strong acidic sites, the byproduct ethanol dehydration reaction occurs. In summary, it should be said that the rate of the highest rate of formation of butadiene and the lowest rate of byproduct formation are
Olga, your time is
yes,
okay.
1 minute. And the highest rate of butadiene formation and the lowest rate of byproduct formation is observed over the samples of magnesium containing with the modification of cerium, and over the zirconium containing samples with the modification of yttrium. Some conclusions there is on the slide, and thank you for your attention.
Okay, thank you very much for your interesting speech. And who has questions to Olga? Not questions? Okay, I have a small question.
I have a question.
Oh, okay.
Vovka Zamirevna.
Okay, please.
Olga, very interesting results, but the yields of butadiene on your samples not very high, unfortunately. Can you separate your products?
Yes, the yield of butadiene is quite small, but we specifically studied the process at the constant ethanol conversion of about 8% and 35%. That's why. And for about the distinguishing the products, our catalytic experiments were made in the quartz reactor with the subsequent identification of the products in the through the Haz chromatography over the capillary column FAP, HP FAP.
Okay, as I see on this slide, you use fixed bed flow reactor, but maybe would be interesting to use continuous flow system for your investigation. What do you think?
We studied in continuous
recirculation of the products.
Yes, it will be interesting, but now we did not make some experiments. We plan to do this.
Thank you.
Thank you. And the questions, please. One small question. What do you think the selectivity of your catalyst achieved because of the difference of redox activity, additional elements, or because other reasons?
The active sites, as we can see on the slide, this process of production of butadiene consists of the several reactions, and for each of reaction we need specific type of sites. And for the first reaction of ethanol dehydration to acetaldehyde, we need the basic sites, or the zinc oxide can be as the dehydrating additive. And for another steps of the process, we need the acidic sites, and these sites we formed with the modification. It's magnesium containing sites, zirconium containing sites, and the sites with rare earth elements.
Okay, thank you. Very interesting. Yours was your speech, and now it's okay. Thank you, Olga. And our next speaker, Viktor Kisluk from Kurdyumov Institute of Metal Physics, NAS of Ukraine. Please, Viktor, are you here?
Yes, I'm here.
Okay.
Thank you very much for your presentation,
Okay.
Mrs. Chairperson. Dear audience, I'm Viktor Kisluk from Institute of Metal Physics, as kindly presented by Chairperson. And I would like to make the presentation entitled Structural Anisotropy of Ethylene Vinyl Acetate Film. First of all, is it clear? Everything is seen?
Yes, we can see you clear. And
okay, so then I will proceed. The outline of my presentation includes some brief characterization of the material. I make some introductory remarks about why we study this material and what are the attractive moments of this material, and why it worth be studied deeper. First of all, I will represent our results on tensile testing, mechanical testing as traditionally developed in the Institute of Metal Physics, and some techniques are used for studying this unusual for us polymeric systems. And it includes tensile testing, creep of polymer. We previously oriented. I will then discuss why we do it, and make X-ray diffraction and nuclear magnetic resonance, and all these techniques demonstrate the anisotropy of properties of the material. And also we discuss some behavior of the molecules, which are witness of what happens inside. It's the so-called Hall's molecule, the hindered amine light stabilizer molecule, used in photovoltaic encapsulant to reduce the impact of ultraviolet on the integrity of the film. And also we consider the oxidative behavior, of the film. And finally the conclusion. So first of all, my pleasure to introduce my colleagues who participated with me. It's the team of from various institutions of National Academy of Science of Ukraine. First of all, the Institute of Metal Physics, the main core of this team. It's Shivanyuk, Rudj, Kotrechko, who make research, make very useful remarks. This Voronoi Igor from Leshkarev Institute of Semiconductor Physics, who proceed electron paramagnetic resonance measurements, and Trachevsky Volodymyr with nuclear magnetic resonance, deep help and the interpretation of the results. So this material has the structural formula presented here. It consists of two main counterparts. It's polyethylene, PE abbreviation, and vinyl acetate. And it also recognized by nuclear magnetic resonance technique, as shown at the right hand graph. And we can identify the features of this spectrum with the structural formal fragments. And the dominant feature is the main polymer chain of polyethylene, A2, it indicated as A2, and the vinyl acetate is A1. And what is the one of the main feature, the peculiarity of this material, its properties can be modified by various content of vinyl acetate group. And for our application, we studied the photovoltaic encapsulant application. It contains 28% of vinyl acetate. Vinyl acetate also has another advantages, electrical resistivity and so on, and very good optical transmission, and can be used in various techniques to produce with other materials, composite materials, and it defines its applications as in food industry. It means that many shoes can be made of this material. It's a carpet for automobile, the enclosure of safety helmet, and the isolation for cable, electrical cable, and of course our special interest, the film who protect the photovoltaic modules. And a lot of another research demonstrated the very effective and unexpected behavior of this material when it combined with nanospecies like nanoparticles, nanocarbon, allotropes, and so on. And it can also modify a lot of the main properties of the film. And we also hope that proceed with this kind of composites. And initially, it is synthesized as granules. And just a few words. It's not my. It's our objectives why we choose this material, because our general objective is rather ambitious, and we try to learn how to predict material service life. It's as many researchers in the world, but of course it's global objective. It has its own subtasks, and we look for appropriate models and experimental techniques to study how degradation starts and how we can follow the phenomena in predicting this degradation. So we need parameters and witnessing aging signaling of the degradation process, and also accompanying phenomena. And we now at the beginning of including this phenomena in our consideration. So a few words about the technology and why the anisotropy we expect from these films, because this is the very brief and schematic representation of how this film can be produced by extruder technique, extruder and molding machine. And these granules synthesized just fit into the extruder and elongated through the some nozzles, and makes the film, which is wound in rolls, and the producers deliver this kind of product in the rolls. So we consume it in the roll, and you see some kind of elongation, some kind of anisotropy also is expected in the film itself. So then the process, even the process of curing, so-called vulcanization, is creating of some transversal bonding between the main chains. It can avoid this anisotropy, and I will show and follow in the following slides. And first of all, it's dynamic load. As we apply the load of near 22 newtons parallel and perpendicular to the orientation of the film, we immediately feel observe the anisotropy. The creep time, the time till the fracture of the sample, it differs many orders of magnitude. For parallel, it's 30 minutes, and for perpendicular, it's only 2 seconds. So it's rather the first trigger point how to proceed, why we proceed this results, proceed this investigation. So tensile testing showed in our previous research that there are 2 stages, and our attempt to describe the creep time, tau, creep time with the simple formula of Zhurkov, it's not valid here because we clearly seen 2 stages, and we just choose the second stage, stage second, which corresponds to aligned state of the polymer. And with this polymer, we make the experiment with tensile creep. Creep, it means subjected to the load under some time till its fraction, the constant load. And we will see that usually in such materials, there are 2 splitting points, as shown at the right graph. Right graph is just recalculated the experimental data on force, which at the axis axis is force, and we study it and graph it, plot it in stress terms. And in stress terms, it means that we include the cross section, and there are 2 splitting points. Splitting, it means that under dark and under ultraviolet accidents, the path of these graphs differs, and it differs from some point. And for parallel orientation, the creep time, the splitting point of creep time dependence, it starts at higher values of the stress, whereas at parallel, at the perpendicular direction, this splitting point is happens at much lower values. This is the manifestation of this anisotropy in such experiment in creep time. So this is the amorphous and crystalline material, and so as shown in this electron microscopy pattern. And we studied the anisotropy of X-ray diffraction of nanocrystals, and so we reduce the whole spectrum to the same intensity of the main replica at 110 Miller index. And what we see at the higher indexes, we see that the huge difference between normal and parallel orientation for the sample. We see that the replicas have higher intensity for 011 and 201 and so on at this range, these replicas. So anisotropy of the film dictates anisotropy of the nano crystals present in the film. So nuclear magnetic anisotropy in proton resonance, a so-called broadline spectroscopy, which based on the analysis of the spectra as they are. It means that there's always some natural widening of the component resonances. It associated with momentum interaction in local field, and this stochastic deviation of the local field, it dictates the widening of the general peak. And we see that in parallel, we see the whole presence and wider lines, as shown at the explanation at the right below graphs. But in perpendicular, the dynamic of side acetate group, it becomes so huge. As the dynamic determines the narrowing of the spectrum, and we see that this component is enormously narrowed for the perpendicular direction. This means the anisotropy of the molecular dynamics of the polymer as whole. Also, we concentrated on the presence of additives, and we tried to use some additives which can show the paramagnetic properties, because paramagnetic resonance is very sensitive. But photovoltaic encapsulant, there are the hindered amine light stabilizer, which is the radical sweeper. So the radicals responsible for the ETR signal, there are very few even after the huge impact of ultraviolet, because this is a very brief representation of the scheme how the Hall's molecule can be regenerated at the presence of oxygen, and it sweeps, it removes the radicals produced by ultraviolet and mechanical stress, and again regenerates to its previous form, and almost totally. But there is still some residuals, and we demonstrated that Hall's molecule, its nitroxyl state of this molecule, it demonstrates triplet, but triplet with some hindered component. One of the component is much lower intensity, as shown, the right one, and it is modeled with anisotropic spectrum, and we demonstrated that this asymmetry is associated with the anisotropy of the molecule itself. It can be explained, but this Hall's molecule is also the spy, which make us the chains to look inside.
Professor, but your time is out.
Sorry?
Time is out now. We have a limit time, only 15 minutes with questions, but you speak 20 minutes.
Sorry. Then I just few reminders about the one more phenomenon we demonstrated in our research. It's oxatic phase. It means that at some kind of strain, some extent of strain, we have the phase when the Poisson ratio is negative. It means that deformation leads to the increase of the transversal dimension. So, in the conclusion, and we also associate this phenomena with the anisotropy of the film. So, in the conclusion, we demonstrate two kinds of anisotropy of this film. The first one is associated with the structure orientation predicted by the technology, as it manifests itself as nanocrystal orientation, anisotropy, oxidative behavior, and also molecular anisotropy revealed as in Hall's stabilizer molecule. This is acknowledgement to National Academy of Sciences for their support and Professor Microscopy for help in electron microscopy experiment. Thank you for your attention and sorry.
Okay, thank you very much for your very interesting speech. And colleagues who has questions, please, the questions.
I have some remarks. Possible?
Of course.
You investigated polyethylene, not ethylene, by polyethylene vinyl acetate.
Well, yes, it's your remark is quite appropriate, but I just use the general terminology usually used by other researchers, pioneers in this field. So, but actually, you are right. It's polyethylene and polyvinyl acetate copolymer is the proper term. Thank you. Thank you. It's for your remark.
No more questions? Okay, thank you very much. And now our next speaker, Professor Yuri Sementsov from Chuiko Institute of Surface Chemistry, NAS of Ukraine. Professor Sementsov, are you here?
Yes, I am here.
Okay. Okay, we are ready to listen your speech.
Okay. Good morning. Are you listening? Yes. Good morning. Доброго ранку. Ми з України. Dear ladies and gentlemen,
yes, of course.
For your attention, my report electrophysical and strength characteristics of polychlor-trifluoroethylene filled with carbon nanotubes dispersed in graphene nanoplate with suspension. Just a moment, next slide. Okay. As per two carbon nanomaterials, namely carbon nanotubes and graphene nanoplatelets, GNPs, are great interest. They have expansional electrical and mechanical properties and therefore are actively used as hybrid fillers for the development of new generation of nanocomposite materials. However, their properties are stable and reach a high level only with a sufficient level of dispersion CNT agglomerates. Likewise, poor dispersion and insufficient interfacial bonding limit the effectiveness of using CNTs and GNPs to reinforce polymer matrices. Dispersion of CNTs in laboratory and industrial conditions is carried out by ultrasonic treatment in ball, planetary vibration mills, hydrodynamics disintegrator, etc. To obtain stable suspensions, various methods of chemical modification of the CNT surface are used and surfactant, while surfactants slightly reduce the electrical conductivity on the systems. In this work, it was established that the combined suspension of CNTs and GNPs in water at certain concentration is stable for considerable period of time without the use of surfactants. Therefore, CNTs and GNPs are surface active and stabilizing components in relation to each other under certain conditions. The aim of this work is to optimize electrophysical and physical mechanical characteristics and establish the regularities of the structure formation process of the PCTFE system with hybrid filler, CNTs and GNPs using the equations dispersion of GNPs for dispersing CNTs. Next. CNTs have been obtained by catalytic chemical vapor deposition by pyrolysis of ethylene or propylene with application of metal oxides catalyst. There are two problems in the CVD methods. The first is the supply of the carbon source to the catalyst, And the second problem is an effective catalyst which provides high structural selectivity, those synthesis of crystalline carbon material in the form of carbon nanotubes. The first problem was solved by creating a pseudo-liquid-filled state of catalyst due to the reactor rotation. The device for CVD synthesis of CNTs by catalytic pyrolysis of hydrocarbon in the reactor volume 30 decimeter cube and output about 1.5 kilogram per day is shown on the slide. The complex oxide catalyst was obtained by the resolve method shown in figure 2. Precursor for this synthesis of trioxide is aqueous solutions of aluminum fermiate, molybdenum fermiate, and iron citrate. The optimal composition of the catalyst which gives high quality CNTs is as follows, we see. In figure 4 shows the term picture of multi-wall CNTs. The diameter of CNTs is in the range of 10 to 40 nanometers. The most probable is 20 nanometers. The specific surface is from 2 to 400 meters square per gram. Large-scale production of CNTs, as a rule, the method of vapor deposition gives CNT agglomerates. We see on figure 5 on this slide, with the size of 20 to 500 microns. GNPs was obtained by secondary intercalation of electrodes from expanded graphite foil in alkaline electrolyte of lower concentration with a current transmission from 6 to 60 milliampere per centimeter square. The separation of nanoparticles was provided by a membrane made of polypropylene fabric. Why did you choose expanded graphite? Exfoliated expanded graphite is a group of materials with a graphite-like structure which is obtained by rapid heating thermal shock graphite intercalation compounds and their hydrolyzed forms. Decomposition and evaporation of the intercalates leads to a strong expansions of the particles along the axis perpendicular to the graphene plane. EGs are characterized a complex structure of the developed surface, figure 2 on this slide. Expanded graphite characterizes also the presence of long slit-shaped and cylindrical defects with medium section from 0.7 nanometers to 20 nanometers caused by twisting of one or several atomic layers, as one on figure 3 we can see. Various thermochemical treatment of natural graphite makes it possible to change the structure parameters of products table on slide 4. In particular, is the size of areas of coherent scattering of X-rays. Okay. The structure features of EGE are nanoscale defects and appear in the Raman spectra on slide right, and low temperature desorption of carbon dioxide in nitrogen, slide 5 left. Next. Ladder correlation spectroscopy particle size analysis showed that the GNP sample contains two types of particles, large particles and small ones of about 450 nanometers in size, being more stable. Figure 1, slide 6. The thickness of second type nanoplates is equal to 5 or 7 nanometers. We estimated the plate thickness as equal to 10 graphene layers. Next. The agglomeration of CNTs was carried out by ultrasonic treatment in a dispersion of graphene nanoplates. The GNP's content was 0.1 weight fraction to 1 weight fraction of CNTs. The weight ratio of GNPs to CNTs did not change. 3 ecosystem with CNT content of 0.5 weight percent named as 0.5 and 0.25 weight percent named as 0.25, and 0.125 weight percent were dispersed. The CNT and GNP suspension pre-moistened with ethyl alcohol. The resultant dispersion was dried in a rotary evaporator at temperature of 75 Celsius degree. After removing the water, the resulting mixture was poured into a mold, and samples were formed at a temperature of 232 Celsius degree and the pressure near 5 MPI. In the work composites with the content of hybrid filler CNTs and GNP from 0.0005 to 0.11 volume fraction were studied for each obtained system. In figure 1 left on this slide shows dependence of electrical conductivity of this system on the CNTs and GNP's content. In the interval of 0.001 to 0.005 volume fraction of fillers, in the polymers there is a sharp increase in electrical conductivity for all systems, a phase transition of the second kind, the electric conductor. The analysis of the obtained results was carried out from the standpoint of percolation theory according to the quotient 1, made it possible to determine the value of the percolation threshold and percolation indexes in table 1 PC. A decrease in the content of CNTs in the dispersion of GNPs during their co-dispersion contributes to a more uniform distribution of CNTs in the system with a polymer. This is manifested a decrease in the percolation threshold for system from S0.5 to S0.125 and increase in electrical conductivity around the percolation thresholds, respectively, figure 1 left. A more uniform distribution of the electrical conductive component in the polymer is also confined by change in the exponent T, the value of which decreased from 2 to 1.75 with a decrease in the concentration of CNTs in suspension during dispersion. Table 1, you can see. The results of studies of the real and imagery component of the Composite dielectric constant from the volumetric content of CNTs and GNPs in PCTFE composite systems are given in figure 1 right. It can be seen that component of the composite dielectric constant change non-linearly for all systems in the region of low filler content, approximately 0.001 to 0.005 volume fraction CNTs and GNPs in the polymer, which is associated with the presence of percolation transition and corresponding to its threshold. The strength characteristics of composite system was investigated. Dependence of the relative bending strength limit in composite system on the content of the fillers are shown in figure 2, slide 8. For all three systems, the maximum is observed in the region of CNT and GNP's concentration corresponding to the percolation threshold. Moreover, for more homogeneous systems, the maximum shifts to lower values of the fillers content, figure 2. Analyzing the results shown in figure 2 and figure 1, it can be asserted that there is a dependence between the CNTs and GNP's content and the maximum values of bending strength limit and the value of the percolation threshold. The dependence can be written in the form equation 2, where K, the proportional factor which depends on the aspect ratio of CNTs and uniformity of the distribution of the filler nanoparticles in the polymer volume. Moreover, the values of the content at which the maximum of the relative strength limit are observed almost coincide with the values of the content corresponding to the inflection points of the dependencies electroconductivity on the content of fillers in the region of high value signal values. And conclude. It is shown that the joint ultrasonic treatment of aqueous mixture of carbon nanotubes and graphene nanoplatelets make it possible to obtain the stable dispersion at a ratio of 0.1 weight part GNPs up to 1 weight fraction of CNTs and content in water of 0.5 to 0.125 weight percent of CNTs. It is shown that the percolation threshold in the PCTFE, CNTs, and GNP system decreased from 0.0049 to 0.00098 volume fraction when the content of CNTs in water decreases from 0.5 to 0.125 weight percent during the joint ultrasonic dispersion with graphene nanoplatelets. At the same time, the content of CNTs at which the maximum limit values of the relative bending strengths are observed shifts according to the shift of the percolation threshold. The maximum values of strength limit will be achieved with a more uniform distribution and stretching of CNTs in the volume of the polymer matrices. Thank you for your attention.
Thank you very much for your interesting speech. Okay, yes, Heroim Slava, yes, of course. Colleagues, please, the questions. Who has the questions?
I think time is out, and next lecture maybe have to speak.
Okay. Our next speaker is Alexander Bachechka from Bakul Institute for Super Hard Materials of the National Academy of Science of Ukraine. Please, Professor Alexander, please, are you here? Professor.
I'm sorry, Alexander Bochechka.
Oh, Bochechka.
Not
Sorry, Bochechka.
Not Bochechka.
Sorry, Professor Bochechka. Okay. Are you here? Okay.
I have questions. We have coffee break or my presentation?
Presentation. We had to work. Presentation. Yes, I think presentation because our program needs to listen to speakers.
Okay. Ladies and gentlemen, dear colleagues, I have the honor to represent here the Bakul Institute for Super Hard Materials of the National Academy of Science of Ukraine. The theme of my report is intensification of the compaction process of diamond nanopowder under high pressure and high temperature.
Sorry, Mr. Bochechka, we can't see your presentation.
Do you not see my presentation?
No, we can see only your face.
Oh, I'm sorry. I'm sorry. Moment. I'm sorry. Can you see my presentation?
Yes, but not on full screen.
Good. Presentation.
It's not on full screen yet. Can you please stop sharing the screen, then start your sharing your presentation on full screen, and then share the screen in the Zoom?
Do you see my presentation?
We see, but not at full screen.
Full screen?
Not in full screen. Okay.
But I see full screen.
Yes, because when you start the full screen with already shared the screen on Zoom, it's open another window that we do not see. Okay, let it be like that. We can see it quite well, so you can start.
Thank you very much. The theme of my report is intensification of the compaction process of diamond nanopowder under high pressure and high temperature. The object of our study is a nano-dispersed diamond powder. We have used the statically synthesized diamond. The aim of this work is to increase the compaction degree.
Sorry for interruption once again, but the slide did not change. We still see the first slide.
Not change slide?
Yes, yes. Can you please press escape?
Escape?
Yes.
Yes.
Then try to change the slide again without the full screen mode. Next slide. Yes, now it changed. Okay, let's do it like that.
In this variant or full ekran?
Yes, yes, now we see your next slide, so please continue, yes.
In this variant, yes?
Yes.
The object of our study is the nano-dispersed diamond powder. We have used the statically synthesized diamond. The aim of this work is to increase the compaction degree of diamond nanopowder during high pressure sintering of a polycrystalline diamond composite to increase the level of its physical and mechanical properties. As you know, the decreasing grain size in the mine is the main method to activate sintering in powder metallurgy. But if we sinter the diamond powders, we obtain another result. As the grain size decreases, the density and physico-mechanical characteristic decrease too. In our opinion, there are at least two reasons for this. The first, the difference in direction between external forces acting on the system and internal capillary forces. And the second, the interaction of diamond particles with oxygen and oxygen-containing groups of their surfaces. In the case when the above forces are opposite, the compaction degree decreases, but a mean pressure on the porous surface increases. The graphitization occurs due to the interaction of diamond particles with oxygen and oxygen-containing groups on their surfaces. So, if we want to sinter diamond nanopowders, we need, first of all, to change the functional state of surface of nano-sized diamond powder. As I reported last year at the Nano Conference, annealing in vacuum and argon leads to the removal of OH and CH groups and a decrease in the number of removal of OH and CO groups and a decrease in the number of CH groups. Annealing in hydrogen causes the removal of OH and CO groups and increase in the number of CH groups. The process of tungsten carbon bonds formation on the surface occurs as a result of the reaction of purified diamond nanopowders with 3-oxide powder. Tungsten carbon bonds formed by interaction of sublimated tungsten oxide with carbon atoms on the surface of diamond nanoparticles. The most intensely these bonds are formed during annealing in vacuum at 600 Celsius grad. So the rate of oxidation of the diamond nanopowders decreases as a result of the chemical modification of the surface of diamond nanoparticles by tungsten the formation on tungsten carbon bonds. We usually use a toroid high pressure apparatus for high pressure sintering. The working pressure in this apparatus is about 8 gigapascal. Samples of the composite were sintered at a pressure of 8 gigapascal, a temperature of 1600, 1700 Celsius grad, and a sintering time of 20 seconds from a mixture statically synthesized diamond nanopowder and tungsten trioxide powder, annealed in vacuum, followed by annealing in a hydrogen atmosphere. You can see the result of high pressure sinter of this mixture. First of all, the porosity of the composite sintered from statically synthesized diamond nanopowder at a pressure of 8 gigapascal, a temperature of 1650 Celsius grad, and a sintering time of more than 20 seconds is close to zero. Secondly, the compaction degree of diamond nanopowder increase by 8% due to surface modification with carbon tungsten binders in combination with the gassing before sintering and the reaction of diamond with tungsten. Thus, the modification of the surface intensifies the compaction process of the diamond nanopowder under the action of high pressure and high temperature. We should also dwell on one more important point. Ignoring gas desorption immediately before sintering reduces the hardness of nanocomposite samples sintered from diamond nanopowder modified with carbon tungsten bonds by a factor of 2. As a conducted tests have shown, the most promising used field of diamond tungsten carbide nanocomposite is working elements of tools for processing aluminum silicon alloys. You can see conclusions which I have reported. Slava Ukraini! Thank you very much for attention.
Very much for your very interesting speech. Colleagues who have questions, please, the questions. Nobody have? Yes? Okay, okay.
Yes, we have one question. Who? You?
Sorry, I missed your information about the optimal conditions. What is the pressure at the optimal temperature of 1650 degrees?
I'm sorry, what is the pressure apparatus? Please, your questions.
I would like you to tell about the pressure at the optimal conditions.
Oh, optimum condition?
Yes, pressure of your equipment.
What pressure do you use?
The pressure was 8 gigapascal and temperature about 1700 Celsius grad.
Thank you.
Okay, the next questions? No questions. Okay, and now our next speaker, Alexander, sorry, Volodymyr Prokopyuk, Professor Volodymyr Prokopyuk from Institute for Problems of Cryobiology, Cryomedicine, National Academy Science of Ukraine. Okay, okay, please.
Presentation must be here from yesterday.
From yesterday,
Already,
yeah?
yes, yes.
Just a moment.
Yes, it is. Do you have some?
Yes,
Yeah,
it works.
yes.
Okay, everything okay.
Just a moment, we'll start the sharing to the online, so everyone could see it.
Okay, it's working. Yes. Dear colleague, I'm happy to see you now. I'm happy to take part in this conference. My presentation is devoted to the influence of lanthan orthovanadate drop europium nanoparticles on cell culture. It's a result of collaboration between Institute of Scintillation Materials, Institute of Problem of Cryobiology, and Kharkov National Medical University. Our colleague produced nanoparticles and they study these properties of these nanoparticles in not cellular system, and we do this study in vitro and in vivo. In this presentation, I show how it looks in vitro study of nanoparticles. Oh, I try, but it don't work. I want to see next slide. Okay, oxidative stress, it's one of well-known pathological process. Oxidative stress plays some role and take part in the pathology like aging, infertility, chronic fatigue, atherosclerosis, and lot of other pathological processes. But it can be used also for cancer treatment, and it can be used by immune system for eliminate some pathogen and cancer cells. Typical antioxidant, it's some drugs that can provide the free electron to radical and inactivate it. Usually we use antioxidants like vitamin C, E, A, tannin, flavonoid, and etc. Our colleague from Institute of Scintillation Materials produced nanoparticles with property of pro-oxidant and antioxidant. It's nanoparticles with from gadolinium orthovanadate drop europium and lanthan orthovanadate. Very important that these nanoparticles can change their activity from antioxidant to pro-oxidant. It can be used for example for cancer treatment like radiomodificator or for photodynamic therapy. This means we can inject nanoparticles like that in the organism, and after that we can modify their properties. But usually without modification they work like antioxidant. The aim of our work, this part of research, was to investigate the effect of lanthan orthovanadate dropped with europium nanoparticles on the fibroblast cell culture. Experimental design. In our research, we use mouse embryonic fibroblast. In these pictures you can see monolayer of these cells. Usually these cells make monolayer on the culture dishes. These cells has all typical life properties. They can keep their integrity, they can react to the environment, they can reproduce themselves, and they can even move on the plastic, then they have the property of adhesion. Fibroblast is a typical cells of connective tissue, and connective tissue are present in the lot of organ and tissue. In our study, we incubate these cells after monolayer formation for 24 hours with different concentration of nanoparticles, from 30 microgram per milliliter to 520 microgram per milliliter. Control was cells without nanoparticles. After that, we do 6 different screening assays to study all typical property of these cells. First of all, we use light microscopy for study the shape of the cell, the confluence of monolayers. Confluence, that means which part of the plastic it's covered by cells, adhesion of cells, and membranic integrity. The next assay, it was a scratch test. Scratch test, it's a test for cell migration. After monolayer formation, we do some defect on monolayer, and after that, we measure the speed of the cell migration on this defect. The last picture, it's a study for genotoxicity, micronucleus assay. Usually, after cell division, we can see micronucleus, but if some drug has genotoxicity, we can see macronucleus. It's a photo of cells treated by drug with platinum for cancer treatment. It's a drug, cisplatin, that can methylate DNA. Next 3 assay, first of all, it's MTT assay. MTT assay, it's a metabolic assay. MTT reactive can be converted to the formazan, it's a black one, only in mitochondria. Nitrile red uptake assay, it's assay for cell spinocytosis, because this substance can be absorbed by cell only with spinocytosis. And the last assay, it's a proliferation assay, doubling time population. We measure the time when the cell number became bigger in 2 times. In these pictures, you can see the cells shape, confluence, and adhesion. You can see that there is no difference in the low concentration of nanoparticles. But when in the high concentration, from 65, 130, and 520, we can see that cells change their shapes. We can see some space between cells, and in the highest concentration, you can see all cells are detached from plastic. That means cells already die. No, it's absolutely toxic concentration. In these pictures, you can see the diagram of confluence, percent of plastic covered by cells. In the low concentration, all plastic, 100% were covered by cells, and the concentration 65, 130, confluence decrease, and in the highest concentration, already we haven't seen cells on the plastic. All cells were detached. Membrane integrity, we measured membrane integrity using staining by trypan blue. Trypan blue, it's a substance that can go into the dead cells. Where membrane is good, it's work, all channel, ion channel are working, cells don't stained by trypan blue. You can see that even in the high concentration, a lot of cells keep in membrane integrity. That means some cells that already detached, but membrane are still working. Next test, it was natural rate uptake test. It's a test for pinocytosis. Pinocytosis, it's active endocytosis of some substance. You can see that in this slide, only high concentration affect this process. And if you can see the photo, even round-shaped cells they are stained by natural red. That means that cells that already lose adhesion, they will die, but they have still ability to pinocytosis. The same you can see when we do MTT test. MTT test, it's a test for activity of mitochondria, its metabolic activity, the same. Mitochondria in the cells works even in the high concentration of nanoparticles. And in the picture you can see even round shape and detached from the plastic cells. They are black. That means there are formazan in these cells. Scratch test, it's a test for cell migration. You can see that that low concentration even stimulates the cell migration. And concentration from 130 and higher sharply decrease the cell migration. Proliferation assay, how many division make cells per sometimes reflect that low concentration of nanoparticles even stimulate cell division, and high concentration block this process. The last one is genotoxicity. We haven't found genotoxicity of these nanoparticles. The photo with control, it's photo with it's positive control with cisplatin. It's not nanoparticles. Conclusion. Lantan ortovanadate dropped European nanoparticles demonstrate no genotoxicity against fibroblast culture in vitro. Nanoparticles have a cytotoxic effect on fibroblast at concentration greater than 130 microgram per milliliter. First of all, proliferation, adhesion, migration changes, mitochondrial function and lysosomal function are less sensitive. I have to say some word about nanoparticles with gadolinium ortovanadate. My colleague described these nanoparticles yesterday, but using eryptose. Lantan ortovanadate a little more toxic, but the difference, it's not big difference. I mean, this may be the same result, but the difference in lantan after statistical processing is a little bit more significant, but not a lot. Okay, thank you for your attention.
Thank you very much for your very interesting speech. And okay, the questions, please.
Just a moment.
Включила.
Microphone. Tell me please, what information did you obtain from scratch test and how it relates to your material?
No, thank you for your question. Scratch test is a test for cell migration. When we have free arrows to the plastic, the typical reaction of the cells is cover all area. We can see, we think now if small concentration of nanoparticles stimulate this parameter and they stimulate the proliferation, we can, we think that this, for example, these nanoparticles can be used for wound healthing. because when you have wound it, okay, it also might be covered by fibroblast, and wound might be covered by proliferating fibroblast.
Okay, thank you. Next questions, please. No questions? And I have a small questions. Why do you choose orthogonadates? And the first questions, and as I understand, you tell that about injections of nanoparticles in living organism, but is a big problem to removing from living organism nanoparticles. And what is about this problem?
Why we choose orthogonadate? It's our colleague from Institute of Scintillation Material has big project with orthogonadate. They already study this nanoparticle in not cellular system, and they have a question about studying in live system. It's they. From removing, I don't know. We have to do some.
Very, very big problem, because we work with this different same materials and have problem with removing.
We can do this assay if you saw the previous speech of my colleague. He demonstrates the confocal microscopy of these nanoparticles. Europe can fluorescent, and we can find these nanoparticles using this method.
Yes, I understand. Yes, I understand.
Maybe it can be
helpful. I will tell that living organisms has not mechanism to removing nanoparticles. When cation or anionic species it make.
But we don't know for sure, because living organisms have a lot of mechanisms to remove it, lot of xenobiotic. Maybe organism will use some mechanism for some other xenobiotic, and it will work. It's a problem of living organism. We never know which reaction it will be, which by mechanism it will use.
I understand. It was very interesting questions, and we will work about that. Thank you very much. Thank you very much. Dear colleagues, we have a proposition to skip our coffee break because we don't fit in time and our program. Hence, we go to our next speaker, Evgenia Lapko from Charlie University, Czech Republic. Evgenia, are you here?
Yes,
okay.
Yes, I'm here.
Okay, please.
Is it?
Everything's perfect.
Is it okay with my presentation?
Yeah, everything's perfect. Thank you. You could start.
Okay. Good day, dear colleagues. Thank you for the organization of the conference and for the possibility of to present our results. I represent Nanomaterials group from Charles University. We work with fuel cells and electrolyzers, but today I would like to speak about platinum catalyst for proton exchange membrane fuel cells. Sorry. Do you see? I can't see how to change my slides.
Click on the slide once, and then use your arrows on the keyboard.
Okay, thank you. So, as you know, PEM fuel cells is alternative eco-friendly power source, which converts the chemical energy to electricity. And the heart of the PEM fuel cells is the electrolyte or proton exchange membrane with anode and cathode. And here you can see the history of the fuel cells development. And in the end of the 20th century, two important events happens. First one is the creation of the Nafion membrane by DuPont, and another one, the creation of platinum catalyst based on carbon with high surface area. This type of catalyst is very light. It's very active, and it gives possibility to minimize the amount of platinum on the fuel cells. So for nowadays, it's still actual, and the main catalyst which used for fuel cells, it's this carbon-based platinum catalyst covered on the Nafion membrane. So today, fuel cells technology moves to the application and technology development. Here you can see several famous example of the fuel cells application for mobile and stationary subjects, vehicles, and so on. But it looks like everything is working, but still we have several problems which we should solve. And here I would like to speak about, today I would like to speak about the durability of the support of the catalyst on a cathode and anode side, which influence on the stability of fuel cells work. So as I said, the standard support for catalyst is a Vulcan carbon with high surface area, but also we tried several other carbon-based support. But I want to concentrate your attention on the poly-based nanotubes, which has several types of nitrogen in their chemical structure, and it's supposed to be very stable under electrochemical potential. So we decorated our carbon-based supports with platinum nanoparticles using polyol method, and here you can see several examples of this platinum decorated catalyst. Here is a Vulcan, and here is platinum nanoparticles on the polypyrrole nanotubes. All platinum nanoparticles has the crystallinic structure. It's quite uniform, has a high surface area. But what's to notice that the size of the nanoparticles and the size distribution on the platinum nanoparticles depend on the support which we use for the decoration. For polypyrrole nanotubes, the size of the platinum nanoparticles is from 4 to 6 nanometers, which is small enough to be active in electrochemical reaction, but big enough to be stable under the electrochemical corrosion of the materials. So let's look how behaves the support under the degradation test. So we cycle our catalyst in the range of potential. We simulate the startup and shutdown regime of fuel cell work when this carbon-based support degrades a lot. So we measured this cyclic voltammogram, and knowing this area, hydrogen absorption peak on a platinum, we can calculate how much active platinum we have. So let's look on the standard catalyst platinum on Vulcan. You can see that during the 5,000 cycles, this peak decreased a lot. It means that the amount of platinum active sites decrease. Why it happens? Because we influence on the degradation of the support. So it means that the support degrade, the platinum detach from the support and fall down from the electrode. Also, this, you can see the double layer, which also decrease the capacitance of this double layer increase with the cycling. So it means that the surface area of our catalyst decrease. So it's also say about the degradation of volcan and detachment of the platinum. So, but look on the polypyrrole nanotubes. It was actually unexpected for us that it will be really good. If you look on the hydrogen sorption peak, it almost does not change, for example, in this case. And in this case, it's even increased. It means that something happens with platinum. There are two possible reasons. The platinum, like we observe something like a cleaning process of the surface of the platinum, and also platinum somehow could restructurizate and create more active sites. And also, if we look on the double layer, it does not change. So during the 5,000 cycles, in relatively high potential range, we did not degrade our polypyrrole support. So let's look on the absolute values. So you can and compare it with other platinum particles on the different supports. And you see that really on the beginning, the platinum on volcan is very active, but it degrades a lot with the cycling. And nitrogen doped carbon-based support is quite stable during the time and has have a quite high electrochemical surface area. So, and when we normalize it, we can see that the percentage of degradation of the volcan reach almost 86% during the 5,000 cycles. Other supports demonstrate lower degradation rate. And for polypyrrole nanotubes, it's even like in minuses. As I said, it's because of the cleaning process and restructurization of the platinum particles. So it's our hypothesis, and now, sorry. Okay. What about the activity? Because it can be stable, but is it active enough to be to produce enough electricity for fuel cells? We know that platinum could react with oxygen and hydrogen to produce water molecules, which is the main process in fuel cells. And like a parallel process, it's a producing of hydrogen peroxide, which is a poison for membrane and poison for catalyst. So we measure this using rotation ring disc electrode technique. And we measure this before degradation test and after degradation test. On the disc, we measure the activity of the platinum, and on the ring, we measure the amount of the hydrogen peroxide producing during the reaction. So let's look on the one speed and compare. So what happens for volcan? There are two parameters which characterize the activity of the platinum, of the catalyst in the electrochemical reaction. It's halfway potential here and limiting current density here. So in case of volcan, both parameters decrease after degradation, significantly decrease. And also, if you look on the hydrogen peroxide production, we see some traces of the hydrogen peroxide, which is actually a small amount. Of course, it's increased a little bit after the degradation. Sorry, here I have a mistake, it's opposite. But it's not so critical for fuel cells work. But look on the polypyrrole. Here, the halfway potential almost does not change. It's really tiny changes. And the rate is quite big, 0.8 is quite enough to be active in fuel cell reaction. And the limiting current density is the same. Here for polypyrrole with more amount of platinum, plus minus the same. Okay, the halfway potential is smaller because the active surface area of platinum smaller because of the bigger size of the particles, but still it's quite good and did not change after the degradation. And the amount of hydrogen peroxide produced before and after degradation is quite tiny. So here you can see the summary of the all activity parameters for platinum on polypyrrole, and even after the degradation, it's enough to be active in fuel cells. So why it happens for polypyrrole? Because when we precipitate the platinum nanoparticles on the polypyrrole, some platinum sit on the different types of nitrogen on polypyrrole nanotubes. But after degradation, some platinum remove from the nitrogen peaks and from the one type of nitrogen and move or precipitate or fill some phases to the ideal form to the another, for example, pyridinic type of nitrogen. So it's quite interesting observation, which needs to be finished with some structural measurements, but still it's explain us a lot what happens on the platinum on the catalyst. So we understood that support is quite stable. Platinum is quite active.
Sorry,
but
dear
how...
doctor, but your time is finished.
Okay, I finished. We tested in real fuel cell, and it's demonstrate us quite good performance. So it's quite promising catalyst for real application. I would like to thank my colleague for the measurements and you for your kind attention.
Thank you very much for your very interesting speech. And the questions, colleagues, please, the questions. Who has the questions? No questions?
Yeah, there is a question.
Okay, okay.
Thank you. My question is about the following. You told us about deterioration in electrochemical characteristics of materials that you use, and mainly they were carbon-based material, as I understand, and you only said about nitrogen containing materials at the end of your presentation, but you didn't said about nature of degradation of these other carbon-containing materials. Could you something say about this?
Yes. Actually, I have the summary like this. In the end of the presentation, I told about polypyrrole based catalyst because it was the most stable and the most active in the electrochemical reaction. That's why, but other carbon-based support is not so stable. As you can see here, is not so active. This parameter is quite low comparable with this, twice, even 3 times lower. So it's good, but not good enough catalyst to produce enough electricity in fuel cells. So we concentrate our attention on this polypyrrole-based catalyst. So it's stable and more active, comparable with others.
Okay, thank you very much. Next questions?
Thank you.
No questions. Okay, so I introduce our new speaker, Alla Dyanchenko from Chuiko Institute of Surface Chemistry of NASA of Ukraine. Dr. Alla, are you here?
Yes, I hear you.
Okay.
Try to share my presentation.
Okay.
Oh, it is visible?
Yeah, great.
Okay.
Thank you.
Okay. Шановні пані та панове, dear ladies and gentlemen, let me to present to your attention the result of work, actually a small overview of the results of work on the development and investigation of effective catalyst for the CO2 hydrogenation process. This, at a first glance, simple reaction of the interaction of CO2 with hydrogen allows obtaining hydrocarbon compounds of various classes. Obtaining the target product depends on the reaction condition, temperature and pressure, and especially the catalyst. The goal of our investigation was methane obtaining. It's not in reality Sabatier reaction is of particular importance as it allows to obtain methane using a carbon neutral technology, while at the same time utilizing the greenhouse gas CO2. Traditional catalysts for this reaction are noble and transition metals. The first class are too expensive and the other are cheap, but have a low lifetime. The improvement of this problem is the use of bimetallic composition, where each component improves the action of the other. We focused our investigation of bimetallic nickel iron and cobalt iron bulk catalyst, and particularly cobalt nickel. The study of activity of this bimetallic composition in the methanation process made it possible to determine the composition that contribute to the effective CO2 conversion into methane under atmospheric pressure is a temperature range of 300–350 degrees. This composition of nickel, nickel iron and cobalt iron is presented of these pictures with you can see highest yield of methane in this point and in this point. We also noted the differences in surface morphology for active and inactive bulk nickel iron and cobalt iron catalyst. The surface of active catalyst has like a sponge structure, while inactive catalysts have a smooth, like volcano surface. It can be resumed. The structural heterogeneity has a positive effect on the catalytic activity of bulk bimetallic compounds. Thermoprogrammed desorption mass spectrometry analysis allowed us to propose a mechanism of methanation of bulk catalyst, which in our opinion occurs by direct hydrogenation of carbon, what is formed as a result of dissociation of CO2 over the active sites of the catalyst. Bulk catalysts have some disadvantages. For example, tendency to cooking and low temperature stability. To eliminate this problem, the catalytically active phases were applied to the carrier. This makes it possible to obtain a higher surface for the activation of reagent and, as a result, a higher product yield. Does this approach work for our active bimetallic nickel iron and cobalt iron composition? To obtain supported catalyst, we used a variety of supports, which can be divided into two categories: carbon-based and inert oxide. Carbon fibers, ultra-dispersed diamonds, graphite nanoplatelets, and carbon nanotubes were studied among the carbon ones. Let's talk more detail about the results of research on catalysts synthesized on carbon nanotubes. The original, the pristine nanotubes show very little activity in the methanation reaction due to the presence of a small amount of metallic nickel in their composition. However, the reaction products over this support are methane and carbon monoxide. Nanotubes modified with bimetallic active compounds contribute to the complete conversion of CO2, and the yield of methane is in the range 60–80% at 350–400 degrees. The series of efficiency looks like nickel iron, next cobalt nickel, and the last cobalt iron. According to the scanning electron microscopy data, the distribution of active bimetallic mass on the surface of the nanotubes is uneven. It is visual big part of bimetallic actives on the end of some individual nanotubes. The analysis of the results of thermoprobable desorption mass spectrometry study indicates the formation of an additional product besides methane. It could be acetaldehyde. The most popular group of catalyst carriers are inert oxide, in particular silica, titania, alumina, and their mixture. Their variable dispersion and chemical inerts opens the way to the controlled creation of nanocomposite catalysts with specified properties. Will such a carrier be able to improve the efficiency of bulk catalysts? The comparative diagram shows an advantage of bimetallic catalyst, cobalt nickel, nickel iron, and cobalt iron, compared to monometallic ones, nickel, cobalt, iron. When applied to the surface of silica and alumina, the effectiveness of nanocomposite catalyst depends on the composition of the active phase and the type of oxide carrier. For cobalt nickel and nickel ferrum catalyst, there is a clear increase in efficiency when applied to silica and alumina. For cobalt iron, the dependence is completely opposite. Applying to oxide carrier contributes to the degradation of the catalytic activity compared to a bulk catalyst of a similar composition. Here it is bulk cobalt iron. Here it is supported cobalt iron over silica and aluminum. In the case of bulk cobalt iron, we have full conversion CO2 to methane. In the case of supported catalyst, we have yield of methane rather low than for bulk catalysts. Thermodesorption profile or desorbed particles from the surface of applied bimetallic catalysts indicate that the mechanism of methane formation on the surface of nanocomposite catalyst is definitely different from the bulk catalyst and proceeds with the formation of oxygen-containing intermediate compound, such this type. In this way, we can give an answer to the question posed by this report. Apply an active nickel iron and cobalt iron composition of the metallic catalyst to the surface, or carbon or oxide carriers improves their efficiency in the methane production process. And cobalt iron biocatalysts work more efficiently than their composite followers.
Thank you. Okay.
I would like to thank Taras Shevchenko Kyiv National University because it is alma mater of this work, and Institute of Physical Chemistry of Polish Academy of Science, especially group of cooperative catalysts, for give me support in this hard time for Ukrainian scientists. Thank you very much for attention, dear colleagues.
Thank you very much for your very interesting speech. And okay, and the questions, colleagues, please, the questions. Who has the questions? No questions. Okay, one small questions. What do you think? What is the best catalyzer among all you proposed? Which has the best properties?
I think for industrial purposes, the best catalyst is very cheap, very productive for methane. It's a joke, but I think it's our opinion. It is nickel iron supported on aluminum.
Thank you very much. Thank you very much.
Thank you.
Yes. Okay. And our next speaker is Mikhailo Kurmach, Pisarjevsky Institute of Physical Chemistry, Ukraine. Dr. Mikhailo, please, are you here? Yes. Okay.
Yes. Good day. I'm glad to see you in this room. And my presentation is about Bio-villiger oxidation. Can start? Lactones is a special class of organic compounds which can be used in different industries, predominantly as precursor for obtaining different plastics, the most as food additives, or as part of drugs or biological active compounds. The most known compound from this class is epsilon caprolactone, which uses as component of nylon 666 as plastic. Typical method for production of lactones is mild oxidation of cyclic ketones by Bio-villiger oxidation. Bio-villiger oxidation is mild oxidation of ketones using different oxidants such as peroxyacids and so on. Such peroxyacids are quite toxic and hard to and ecological non-friendly. So last time investigators can develop new methods using different ecological friendly oxidants such as hydrogen peroxide or peroxides of different alcohols. For this reaction, it is necessary to some catalysis. Last year, last decades, many different catalyses based on Lewis and or Bassett acids are used for this process. For example, tin, aluminum containing zeolites are one of the best catalysts of this process. However, catalytic activity of such compounds are quite high, but in case of bulk molecules, which are could be used in different pharmacy process and so on, their activity is not enough for quite good proceeding of the process. So due to low accessibility of acid site for bulk molecules. So development of new heterogeneous catalysts with developed external surface and with high concentration of acid sites on the external surface of this available for bulk molecule is quite important task. So the aim of our work is to develop new effective catalysis for process of Bio-villiger oxidation of cyclic ketones to corresponding lactones. As objects, we have chosen some different aluminum, tin, and ferrum and zirconium containing zeolites, which we have obtained by direct method. We have obtained them in fluorine, non-fluorine media, and so on. These hierarchical zeolites we obtained using Gemini type surfactants as structure directing agents, which you can see on this slide. These molecules provide both structure direction role and limit growth crystal in one or two directions. The low space in which crystal growth proceeds allows to obtain nanoparticles of zeolite or nanostructured zeolites. In our work, we obtained both both tin and zirconium and aluminum, aluminum ferrum containing zeolites. For example, in the absence of zeolite, in the absence of cation aluminum or boron, we have obtained ferrum, tin, and zirconium containing zeolites with MTV and MPI topology. These zeolites consist from nanoneedle, which are agglomerated in different sponges. In case of, in the presence of boron or aluminum in the reaction mixture, we have obtained bor aluminum bore, aluminum, tin, and zirconium containing zeolites with morphology with nanosheet or nanosponge morphology, which depends on template that we can use. Tin and zirconium containing zeolites are typical Lewis acid sites, so they have only weak Lewis acid site. Addition of fluorine in reaction mixture allow to improve concentration of acid, Lewis acid sites, and incorporated in cation, which are incorporated of tin and zirconium, which are incorporated in crystal framework. When we have aluminum, tin, or boron, aluminum or boron containing zeolites, we have also Lewis acid sites and Bronsted acid sites formed by aluminum, which is incorporated in crystallite framework. As we can see that concentration of Lewis and Bronsted acid sites is higher for zeolites with nano sponge morphology in comparison with zeolite nano sheet. Also, we have established that with increase in concentration of tin and zirconium in reaction mixture and consensually in sample, we have increase in Bronsted acid site for aluminum stannum containing zeolites, while for aluminum zirconium containing zeolites, concentration of Bronsted acid site is decreased, but significantly increased concentration of Lewis acid sites. Why this is important? Because the main activity in this process is made by Lewis acid sites of zeolites. As we can see, we tested our samples in predominantly in reaction of oxidation of cyclohexanon to epsilon caprolactone. Caprolactone is the main and target product of this process, but possibly it could be other products of oxidation by peroxide of hydrogen. For example, one of this product is 6-hydroxy hexacarbonic acid. This is product of cleavage of cycle epsilon caprolactone. As we can see, stannum MTW zeolites obtained in the absence of aluminum and boron ion in the reaction mixture provide moderate activity, which increased with increase in concentration of tin in reaction mixture, and also with increase with addition of fluorine ion cation at addition of fluorine ion at the similar tin contained in the reaction mixture. As we can see, for the first time, that zirconium containing zeolites with MTV topology are more effective in this process in comparison with tin containing zeolites. Ferrum zeolites with MTV and MFI topology are less active in this process, and conversion of cyclohexanon is not exceed 10%. However, concentration, however, selectivity by target product is quite good. Due to low activity of such catalysis, we have not described or investigated them in detail. Also, we investigated aluminum and bore-containing tin and zircony-containing zeolites. As we can see, the highest activity of samples was achieved for aluminum, for natrium and ash forms, hydrogen forms of aluminum zirconium and aluminum tin containing zeolites. But selectivity by target product decreased due to predominantly presence of strong bronzed acid sites, which are presented in some samples. But these samples are prospective for further investigation. So we I have 2 slides. So we have some we have some sets of samples. As we can see, with increase in stannum content, we have increase in conversion of cyclohexanone, and selectivity is by target product is moderate. While in aluminum containing samples, we have peak we have the maximum activity for samples with stannum 18. And we have obtained that addition to this obtaining such samples in fluoride media allows to some increase in concentration, increase in activity of such samples in investigated process. Thus, a set of ferrum, aluminum, stannum, and zirconium containing samples were investigated in this process, obtained moderate tested in the epsilon caprolactam production from cyclohexanone by Bio-villiger reaction. It was shown that the most active samples are beta samples, aluminum zirconium and aluminum tin containing zeolites. And it was shown that using natrium form instead of ash form allows to significantly slightly increase selectivity to target ketone, but activity of such compound are less in comparison with hydrogen forms. I would thank you for attention, and thank you National Academy of Science for supporting supporting these investigations.
Thank you very much for very interesting talk. And the questions, please, the questions. Who has the questions?
We have one question and a poll.
Ой, боже, осторожно.
You said that you receive nanoneedles combined in the particles of different shapes. Can you control the shape of these nanoparticles during the synthesis?
Yes, we can. Yes, we can control the shape of the nanoparticles which we have obtained during the synthesis by varying the structure of the structure directing agent and its hydrophilic part.
Does any correlations between catalytic activities of these nanoparticles during the time of catalytic processes?
Yes, with increase of time of reaction, increase catalytic activity of such materials. Time of catalytic reaction, increase time of increased conversion and selectivity. But at high times of reaction, formation of byproducts, product of oxidation, not very mild as in that case, but very hard, products of deep oxidation was obtained.
Thank you.
Okay, thank you very much. No more questions? Okay, thank you, thank you. Our next speaker is PhD student Malgorzata Sipniewska. from Institute of Physics, Faculty of Physics, Astronomy, Informatics, Nicholas Copernicus University, Tarun Pond. Please, Malgorzata, are you here?
Yes, yes, I'm here.
Okay, okay. We don't see your presentation. Oh, okay.
Okay, can you see my presentation now?
Yes.
Okay. Good morning. My name is Małgorzata Sypniewska. I'm from Faculty of Physics, Astronomy and Informatics, Nicolaus Copernicus University in Torun. In this work, I will be investigating the optical and morphological properties of polymer matrix thin layer containing metalloquinolates and stereoquinolina by using UV-Vis and IR technique. And I will be also analyzing the photoluminescence properties of fabricated thin films. First, a few information about materials. Heteroaromatic compounds are very rich and diverse group of organic molecules, and one of the most important representatives is quinoline. Its structure includes a benzene ring and fused with a pyridine ring. And there are three regioisomers in which the nitrogen atoms is located in three different positions relative to the benzene ring. The 8 hydroxyquinolina derivatives are a group of compounds with rich and varied activity. These compounds contain the 8 hydroxyquinolina moiety, which is consist of two ring system, carbocyclic and pyridine rings with hydroxyl group substituted at position 8. The 8 hydroxyquinolinas are good chelating agents that form complexes with a wide variety of metal ions such as zinc 2+, cobalt 2+, and aluminium 3+, due to the proximity of the hydroxyl group of the heterocyclic nitrogen. 8-hydroxyquinone aluminum has become a breakthrough element in the production of OLED due to its strong luminescence properties. Alco-free bandgap is about 2.9 electron volt, and its alco-free is used as electron transport layer or light emitting layer in OLED. Next is stereoquinoline. There are derivatives of stilbene. They have two active centers, an ethylene group and an endocyclic nitrogen atoms. The steric dyes is used for electroluminescence, photochromism, as well as in the field of pharmacy. And today, I would like to present the result of measurements of three types of samples. Alco-free with polymer, PVK and PSS, STQ copolymer. In this slide was shown the structure of this stereoquinone copolymer. and new type of material, STQ with polymer, the structure of which is shown in this figure. All thin layers were made using the spin coating method. First, here we have the transmittance spectra from FTR measurements of alkyl-free in polymer matrix. We can observe characteristic vibration modes for alkyl-free in this region. In 450 centimeter to -1 is Ln bands, in 550 to 644 it's Al oxide, and 740 centimeter to -1 is aluminum oxide aluminum. Next, at 1460 and 1493, there are peaks associated with both the pyridyl and phenyl group in alkyl-free. The absorption spectra of alkyl-free polymer twin films are measured in this range. In the case of alkyl-free PVK, absorption is characteristic by 4 bands. First, maximum in 279 nanometer is a B band, indicates the presence of the P band associated with the central metal atoms, in which the P star is more prominent. Next is C and D band in 330 and 344 nanometer. And the last, we have band A at 382 nanometer, is associated with the transition from ground to excited states. For alkyl-free PSS thin films, we can only recognize 3 bands. B band at 278 nanometer, C and D band merge into a single band, and as well as A band at 381 nanometer is very weak. This figure presents the photoluminescence spectra of alkyl-free polymer. Insert our polymer spectra. We can see that after excitation of 325 nanometer of the xenon lamp, the studied thin layers emit a strong green light. The second material is stereoquinone copolymer. These figures show FTR spectra for thin layer of the studied copolymer with 3 different substituents. For all compounds, we observed the similarities in the band's position. These figures show the absorption spectra of the stereoquinone copolymers. And for all copolymers, a band at about 273, it's this band, and a band at about 280 to 305 nanometer are originating from P to P star transition. Bands at around 332 and 350 for copolymer 2 and copolymer 3. And also the band at about 370 for copolymer 1 are assignated to the P star transition of the stereoquinone unit. And here we have the photoluminescence spectra under excitation 340 the xenon lamp. In all spectra, we observe band at about 450 nanometer, which corresponds to PMMA polymer.
and in 500 nanometer correspond to stereoquinoline. The change in the ionic force is also, we can also see this. Finally, I would like to present the initial results for the new material, which is LSPQ with polymer. We use two polymers, Panama here and PVK here, and for two substituent Cl and OCH3. And we can see that the obtained luminescence results are a combination of the LQ3 and STQ luminance spectrum. To sum up, the thin layer of LQ3, STQ, and new materials were prepared in polymer matrix. The thin layers were made by spin coating method on glass and silicon substrate. The properties of the made thin layers were measured, which show that the new quinoline derivatives are a combination of the properties of LQ3 and stereoquinoline. And the obtained results consist of the systematic view of the photophysical properties of metalloquinolates and innovate photoactive materials with a stereoquinoline moiety. In the end, I would like to thank my supervisor, Professor Beata Drkowska-Zielińska, and I also thank you, Dr. Vitaly Smokal from Taras Shevchenko National University of Kyiv, who prepared for us the stereoquinoline and LSTQ compound. And also thank you for your attention.
Thank you very much for your very interesting talk. Okay, who has a questions for Malgorzata? No questions? Okay, thank you very much. And our next speaker is student Dmitro Zhitnik, Taras Shevchenko National University, Kyiv, Ukraine. Please, are you here? Dmitro, are you here? No? Next? Okay, our next speaker, Dr. Dora Zakarian, Francevich Institute for Problems of Material Science, NAS of Ukraine. Dr. Dora, are you here? No? Okay. And our next speaker, Professor Victoria Vorobyova, National Technical University of Ukraine, Igor Sikorsky, Kyiv Polytechnic Institute, Ukraine. Professor Victoria, are you here? No. The silence. Okay, dear colleagues, and we finish our morning meeting. Okay, and we may go to the lunch. Okay, and the next meeting will be at 2 p.m. hours. Okay. Okay. Thank you for attention. Thank you very much, and thank you for help.
Это точно.
So, hello, dear colleagues, and we will start our next session. And the first speaker will be Oksana Balaban with the topic Polymer Coating and Brushes, Electrophysical Study and Application from Lviv Polytechnical National University, Ukraine. So, Ms. Oksana, the floor is yours.
Hello, thank you. Do you see my presentation?
Yes, everything all right.
Okay, so let's start. My name is Oksana Balaban. I am associate professor at Lviv Polytechnic National University. And today my topic, polymer coatings and brushes, electrophysical study and application. Here is the authors of this work. And I would like to start with a little bit information about my department of applied physics and nanomaterial science. At Lviv Polytechnic National University, the head of our department, Professor Anatoly Andrushak, deputy head of department, Bogdan Ventrin. Here is our address, email, phone numbers, and also we have our own pages in social media. There you can find a lot of information about us and about the scientific work at our department. We have two fields of scientific investigation, one of them in the laboratory of nanophysics and nanomaterials. It connected with the investigation of materials for application in supercapacitors, lithium batteries, radio frequency capacitors, and we have a research educational center in which we carry out investigation of isotropic and anisotropic electro-optical investigation of different materials. Now a little bit information about our team. Here our postgraduate student from our department, Applied Physics and Nanomaterial Science. He was responsible for carry out electrophysical investigations together with me and prepared samples for investigations. Here is the Doctor of Science Natalia Mikina and Doctor of Science Alexander Zaichenko. They are scientists from the Department of Organic Chemistry of our university, and they were responsible for synthesis of materials. And here is me. I carry out electrophysical investigations on iPad and spectrometer, and all together we discussed results and circle future of our investigation. And now I want to tell you a few words why did we choose this topic and carry out these investigations. The main idea, because of polymers are very popular due to their availability of synthesis, reproducibility of results, economy, and environmental friendliness. Also, they applied in everyday life in all areas of scientific investigation and in all areas of our life. But today I would like to show you the application in power sources and nanoelectronics, for example. Yes, here you on pictures you can find a variety of its application in supercapacitors, also as electrolyte for supercapacitors and for batteries, lithium-ion batteries, as cathode and anode materials, also fuel cells and solar cells. Moreover, today base of materials for power sources are run out. That's why it is necessary to find new cathode materials, and also there are some requirements for these materials. They have to be, for example, stable and powerful. Also, you know that everyday demands for power sources are growing up with appearance of new devices on market. Yes, that's why we meet with help of these materials, these new requirements. So we choose such type of investigation. As I said, all materials were prepared by our chemists, and now I am as a physician, I would like to tell you how, from physical point of view, these materials looks like. So here you can see schematic representation of these materials. So it like layers, 3 layers. Yes, first here, second and third layers. Where first layer is PBI, second is PVA-MP or poly-VA-WebMA. And the last one layer is the graphene functional polymeric shell. This shell possible to be poly NVP and vinylpyrrolidone or polydimethylaminoethyl methacrylate. Abbreviation you can find here. So here, please. And about measurements. To prepare samples for measurements, we cut a rectangular film with an area of 0.36 square centimeters and produce all measurements on impedance spectrometer after lab firm Eco Cambia and the Netherlands. And all investigations we produce at room temperature in frequency range. Here you can see frequency range of investigation. So a little bit information about samples. We have 6 samples. Here is the information about layers. These 3 layers, for example, every sample has a PBI layer. For example, first sample consists of 100% of PBI layer, and it doesn't have, for example, this polymeric shell. Another example, sample number 6, it consists of 81% of PBI layer, 14% of this layer, and 5% of grafted polymeric shell from polydiamide. So let's go to next page to results and discussion. Here I present results of impedance spectroscopy, and first of all, I should say that these numbers 1, 2, 3 corresponds with number of samples from this table. Here on the left hand, I present low frequency dependence of real part of complex impedance. Low frequency because you can find information about frequency here. Here we have a little bit frequency range. So here we have a low frequency range. As could be expected, the complication of the structure causes some deformation of a low frequency branch of a real part of complex impedance. It means that for samples 1 and 3, we have such as oscillation, which correspond with appearance of inductive response. Inductive response or a negative capacitance, this is normal for the systems with the delocalized carriers. According to general mechanism of this inductive behavior that takes place also even in case when charge are introduced into layers with very small sizes from the range of several nanometers, for example. As follows from this figure, only sample 1 and sample 3 in this frequency range have the localized carriers. From where we find this information, this is because we observe low frequency independence, quasi-independence of real part of complex impedance. Hence, the indicated phenomenon should be expected just for these samples. It follows from the Nyquist diagram. Nyquist diagram is here, for all these 3 samples. And it follows from this diagram that for these 3 samples, the low frequency section, low frequency we have here we have high frequencies, and here low frequencies. Only for sample 1 and for sample 3, we have this inductive response or a phenomenon of negative capacitance. How could we explain this? Because of inductive response can be described as the capture of these delocalized carriers by trapping centers, and they are holding during the time of period of measuring signal. Because we have got this inductive response, we can find application for our materials, so they could be applied in nanoelectronics as active elements of the delay lines, generator-led delay lines. Moreover, you can find the information about polarization properties of samples 1, 2, and 3. Here, a real part of the electric permittivity, and here electrical loss content of this investigation. But we represent investigation in this frequency region. It is interesting for us because we check in this frequency region if we can use these 3 symbols like radio frequency capacitors. For application as radio frequency capacitors, it is necessary a combination of high values of the electric permittivity and low values of tangent of electrical losses. So as you see, low values of electrical losses means less than 1. Here you can find that information that we really in this frequency range obtained very low values of electrical losses, and enough high values of the electric permittivities. Moreover, for sample 1 and for sample 2, we have a normal situation that the electric permittivity decreases with frequency. But something looks like went wrong with sample number 3 because the electric permittivity decreased, but in this frequency range, it behaves something look like anomalous. How could we explain this anomalous behavior of structure number 3? This is explained by the appearance of additional polarization that caused by jumps of carriers of the localized states near the Fermi level. Here you can
Dr.
find
Oksana, sorry, a few minutes left, so please accelerate.
Okay. Here you can find information about samples 4, 5, and 6. Only for sample 6, we have such as oscillation. That means that on Nyquist diagram, we should expect negative capacitance, and here Nyquist diagram confirms this negative capacitance. And such view of covers 4 and 5 means that we have some diffusion processes, which confirms by the appropriate Nyquist diagram for number 4 and for number 5 samples. These structures, number 6, 5, and 4, very useful for application in radio frequency capacitors because they have very high values of the electric permittivity. But a little problem with sample 4 because this sample has high values of electrical losses. That's why here you can find information only about samples 5 and 6. For sample 5, this sample has a high value of the electric permittivity. That's why it's possible to apply this sample as a material for radio frequency capacitors with high Q factors. Here you can find information about the Cole diagram for samples 6, 5, and 4. Such view of Cole diagrams means that it is the birelaxation, and for these two materials we have jointure relaxation or cooperative type of relaxation. A very interesting application of this material in infra-low frequencies because very huge values of the electric permittivity we obtained for samples 4, 6, and 2. Yes, and here we have low losses, less than 1. That's why such combination of polarization properties means that this material is useful as quantum materials, means for quantum battery. So in conclusion, I just want to say that each of our investigated samples are useful for application in power sources and in like nanomaterials for application in as radio frequency capacitors, materials for delay lines, like that, and materials for AC capacitors. And thank you for attention.
Thank you very much for the presentation. Do we have any question in our hall?
Could I ask you a question?
Yes, of course.
You have very interesting impedance curves, and on some of them you have a different relaxation peak. And also on the Nyquist plot, you also have several peaks, which means that different elements from your polymer take part in the conductivity process. Did you analyze what part of your synthesized polymer corresponds to this relaxation peak? Because at different frequency, different part of the polymer chain can relaxate. Did you analyze this?
Yes, we analyzed this. If we look at this table, we can find information about each samples, and we can compare results of impedance spectroscopy with the composition of materials. So, for example, if we complicated this fast PBI layer with a polymeric shell, for example, we obtained a huge, for example, negative capacitance effect with addition of polymeric shell.
Okay, thank you.
So unfortunately, we have no time for another question. So once again, thank you very much, Dr. Oksana, and we will move forward for the next presentation.
Thank you.
The next will be PhD student Pavlo Polishchuk with the topic Structural and Magnetic Properties of Lanthanum Strontium Magnet Nanopowders from Institute of Magnetism, NASA of Ukraine. So, Mr. Pavlo, do you hear us?
Yes, I'm here.
Ah, okay. Это он, запускай.
Это презентация? Так, все верно, да. Все, это мы запускаем теперь. Так. Can we start?
Yes, yes, we can.
Thank you so much. Are you hearing me good? Good afternoon, everybody. I am Pavlo Polishchuk, and I am a PhD student at the Institute of Magnetism, NASA of Ukraine, and MES of Ukraine. I'm glad to be here. Today, I'd like to speak about the structural and magnetic properties of lanthanum strontium manganate nanopowder. It will probably take 15 minutes, I hope. Mixed valence manganetes with the perovskite structure have been studied for almost 70 years. The requirement to create insulating ferromagnets with a large magnetization for high-frequency applications served as the first research driving force. More recent work has been driven by a desire to understand the large negative magnetoresistance effects which appear near and below the Curie temperature. Also, manganetes exhibit a coexistence of different phases, having different electronic, magnetic, and structure properties. I mean phases not in the thermodynamic sense. Okay, examples are ferromagnetic metallic droplets in an insulating background, or insulating droplets in a ferromagnetic metallic matrix. These are the so-called charge stripes. Manganetes with a perovskite structure belong to the multifunctional materials. Let's continue. On this slide, we can see tasks of this work, such as preparation of LSMO nanopowder and investigation of structure, magnetic and magnetocaloric properties of this nanopowder. Here, nanopowders of LSMO were obtained by the Sorgel method from the initial components, as you can see. The annealing process took place for 10 hours at each temperature. Therefore, 5 samples of elasmo at various temperatures are obtained. So, experimental methods. As we know, the fast composition and size of coherent scattering regions were defined using the XRD method. Using scanning electron microscope, the morphology and size of the particles as well as chemical composition were determined. As is well known, the analysis of SEM images using the software Nanomeasure established the distribution function of nanoparticle size. And finally, magnetic measurements were carried in a temperature range from 2 to 400 Kelvin and in a magnetic field up to the 70 kilo-ersted. At figure 1, we see that the main crystalline phase of the elasmo nanopowders is a perovskite structure with a rhomboedral space group. We have obtained spherical nanoparticles of various fractional composition from 16 to 30 nanometers for this multifunctional material of elasmo. And on this slide you can see how intensity depends from the delta. And using the Scherer method, we obtained that coherent scattering regions change from 16 to 30 nanometers. By the way, the BET method was used to measure the specific surface area of particles. Yes, excuse me. It should be noted that the synthesized elasmo 800 sample can be described as a single-phase quasi-monodispersed powder with an average size of spherical particle of 25 nanometers. And our special attention was paid to the study of the multifunctional properties of this elasmo 800 nanopowder. So, magnetic properties. Measurements of the dependence of the temperature dependence of magnetization in a field equal 50 ersted were carried out in two regimes. There are zero field cooling and field cooling regime. The heating and cooling of samples were carried out with a constant rate of 1 Kelvin divided 1 minute. The temperature relaxation time at the point of measurement was 2 minutes. Therefore, the temperature dependencies of magnetization of this of the elasmo 800 were obtained, as we can see at figure 2. It's useful that temperature, that block temperature equal 302 Kelvin in zero field cooling, during zero field cooling. You can ask how it help us. Why is important? Why did it important? I can say that as we know, at when temperature less than block temperature, the magnetic nanoparticle is in a blocked state. Yes, and at temperature more than block temperature, the thermal fluctuation of the magnetization exceeds the difference of the spin states between two energy minima, and the magnetic nanoparticles go into an unlocked state. On this slide, we can see how the temperature, the Curie temperature, we can see how the Curie temperature change все добре? Можна продовжувати, так? Дуже дякую. So, let's continue. Sorry. On this slide, we can see the meaning of the Curie temperature, equivalent of the Curie temperature. Yeah, excuse me. A bit nervous, excuse me, but all good, all okay. For this Elasmo 800 nanopowder, we obtained the 2 Curie temperature. It's important fact, maybe. It's not hard as can be, as we can say, but at first. But when we see on this formula, and on this graph, it will be more more understandable. Thank you. The increase in the extremum of the He divide dt on the zero field cooling regime curves at 328 Kelvin is associated with the blocking of ultrafine nanoparticles, which are in the superparamagnetic state. However, this issue requires further and more detailed studies. And the blocking temperature is the maximum temperature at this curve. Let's continue. As we can see, for determining the effective anisotropy, we write the following equation. From this equation, the value of anisotropy constant equal this value, and it was obtained for the LSMO 800 nanopowder. About the, as I say, about the blocking temperature, magnetic nanoparticles are in a superparamagnetic state with randomly oriented magnetization. The main magnetic parameters of the LSMO 800 obtained from the hysteresis curves. Okay, and next slide, yeah. It's a table one. We can see that magnetization decrease with increased temperature. Magnetization saturation, yes. And residual magnetization also decrease with increasing temperature. And field coercitivity also decrease. The magnetization isotherms of the LSMO 800 nanopowder are well described by the approximation law of the magnetization to saturation. And we have established that depends on the critical sizes. Nanoparticles are in three states: superparamagnetic, single domain, and multi-domain states. It can be concluded that all magnetic particles in the LSMO 800 powder are in the at temperature equal 4 Kelvin are in the single domain state. And magnetocaloric properties. From figure 4, we can see that the magnetocaloric properties were studied using magnetization isotherms near the Curie temperature. And the positive slope of Erod's curves, figure 4b, near the Curie temperature indicates a second-order magnetic fast transition. Using magnetization isotherms near Curie temperature from 280 Kelvin to 400 Kelvin with a measurement state equal to Kelvin, the magnetocaloric effect was determined. The temperature dependencies, as we can see from on this slide, that the temperature dependencies of the magnetocaloric effect in the LSMO 800 nanopowder were determined using the method of numerical integration of the isotherms according to the approximation. With an increase in field, the maximum change in the entropy at its maximum temperature increases from 0.460 at field equal 10 kilostat to 1.818 at field equal 50 kilostat. The relative cooling power parameter writes as in this. With an increase in a field, the relative cooling power parameter increases from this value at 10 kilostat to this value at field equal 50 kilostat. Also in our paper, you can see mechanisms for heating magnetic nanoparticles. And the quantitative and qualitative results are in a good agreement with the Stoner-Wolfart model-based remagnetization mechanism. The most intense heating under an alternating magnetic field is seen for this mechanism when all particles are in the superparamagnetic state. And from figure 6b, in the room temperature range, the SLP in the relaxation hysteresis in the room temperature range exceeds SLP values for the quasi-stable hysteresis, as you can see at figure 6b here. With an increase, it's important that with an increase in temperature, the specific power loss SLP decreases from this value, decreases with increasing temperature. So, conclusions. The critical sizes of nanoparticles have been obtained in different states. It has been shown that the appearance of two ferromagnetic ordering temperatures is due to the influence of the size of ultrafine nanoparticles on the Curie temperature of the bulk material. Near the Curie temperature, the nanopowder has a large magnetocaloric effect, with a predominant contribution from ultrafine particles. The heating of this nanopowder, of these magnetic nanoparticles of this nanopowder in an alternating magnetic field occurs both in the quasi-stable and the relaxation hysteresis regions. Thank you for your attention.
Okay, thank you very much. Do you have any question in the hall or maybe in a Zoom? Yes, we have one question, please.
One moment.
Okay. Добре. As you have said that you use the microscopy, scanning electron microscopy for your investigation, and do you compare the results of XRD, I mean the coherent region calculated, with the size of nanoparticles measured by microscopy?
Thank you for your question. Give me please 1 minute. Yes, as you say, we used scanning and Fey-Magellan scanning electron microscope, and it helped us to know the morphology and size of the particles as well as chemical composition. And we compare sizes of coherent regions, coherent regions, scattering regions, coherent scattering regions, yeah, with obtained results.
Okay, thank you. As we see from the conclusion, you did this work, and I have a small question. You told about this this STEM microscope measurement, but we didn't see this on a slide. So it was done, but you didn't want to show us.
If you thank you for this question, in this presentation you can see a reference from our article, Zeolite, Alexey Valentinovich Pashchenko et al. Multifunctionality of lanthanum strontium manganate nanopowder. And in this paper, you can found references, and you will see what you want.
Okay, thank you. So you just don't want to overwhelm us with this too much information. Okay, thank you very much for this.
Thank you so much.
And we will move forward for our next speaker. Our next speaker will be PhD student Alina Madalina Darabut from Czech Republic, Faculty of Mathematics and Physics, Charles University, with the topic percolation behavior and electrical conductivity in epoxy resined thermally expanded graphite nanocomposites. So, Miss Alina, you are welcome.
Hello. Can you see me? I will share. Okay. Can you see my presentation?
Yes, we see, but not in a full screen mode.
I'm trying. Okay.
Now it's okay.
Okay. Thank you for the nice introduction. My name is Alina Darabut. I'm a PhD student at Charles University in Prague. Also, I'm a member of the Nanomaterials group, and I would like to present my later results on percolation behavior and electrical conductivity in epoxy resin thermally expanded graphite nanocomposites. So for it, I will follow the next outline, and I will start with a short motivation. Our group is working on the development of proton exchange membrane fuel cell components. So as a part of the group, I'm working on the development of the bipolar plates that are one of the main components of the PEM fuel cells. As we observe, if we are develop the properties of the bipolar plates, such as decreasing the total cost, increasing electrical and thermal conductivity, increasing the durability, and improving the mechanical properties, we affect directly to the main targets of the polymer exchange membrane fuel cells. So how can we do this? Traditionally, the materials for the bipolar plate that were used are the metallic and the graphitic materials. But these materials have their own advantages and disadvantages. For example, the metallic bipolar plates are really good in terms of electrical and thermal conductivity, but they have really poor chemical resistance in the PEM fuel cell environment. On the other hand, the graphitic materials, they have much higher resistance, chemical resistance, but their mechanical properties are really low. Lately, the polymer composites could improve all these disadvantages of the aforementioned materials But for that, we have to be careful in the mixture of the matrix and the fillers, in their content. And also, it's important how we proceed to the formation of the polymer composites. So as you may know, the polymer composites is just a mixture between a polymeric matrix, that it's an insulator, and a conductive filler. That could be metallic filler, electroconductive polymers, or carbon-based fillers. In our case, we are working only with carbon-based fillers, such as natural graphite, synthetic graphite, expandable and expanded graphite, carbon black, etc. For the polymeric matrix, we choose the epoxy resin because it's easy to work with it. And for the reaction, we choose an amino group for the cross-linked material. On the other hand, for the conductive fillers, we choose two commercial graphite, the natural and synthetic graphite, and also we have our own thermally expanded graphite. This thermally expanded graphite is obtained in our laboratory from the graphitic intercalated compounds by applying a thermal treatment. During the thermal treatment, the intercalated compound, that in this case is sulfuric acid, it's evaporated and forms the structure of the thermally expanded graphite. More information about the preparation and characterization of this thermally expanded graphite, it's in a paper that it's under review in Advanced Powder Technology Journal. So going back to the different fillers, we have their properties such as particle size and, very important for us, the electrical conductivity. And I will show during this presentation how the different fillers and also their content into the polymeric matrix affects to the electrical conductivity. So for that, let's start with the preparation of the polymer composites. We have the three components, the fillers, hardener, and epoxy resin, and we mix by ultrasonic in acetone solution. After the evaporation of the solution, we grind all the mixture in order to have homogeneous mixture, and we press it using a hot compression molding at 100 kilonewtons, 110 degrees Celsius, and for 40 minutes. And of course, also we have a post-curing process. And we obtain this type of polymer composites that are used for further characterization. And how we are characterize these polymer composites according to their electrical conductivity. We measure the electrical resistance by using 4-point probe method, and we expect to obtain this kind of graph called percolation curve. From here, we have three regions. We have the insulative region, where the amount of fillers is really low, so the level of conductivity is at the level of the polymeric matrix. Also, we have the conductive region, where the amount of fillers is the highest. In this case, the level of the electrical conductivity is on the order of the filler's conductivity. And in the middle, we have a transition region called percolation threshold. That it means that at this percolation threshold, by adding really small amount of filler, we will have huge differences in the properties, and in this case, in the electrical conductivity properties. So furthermore, as I said, we have three different series: natural graphite, synthetic graphite, and thermally expanded graphite. We variated the filler content, and we obtained the electrical conductivity. These are the experimental dots, and using the scaling equation, we obtain also the fitting of these experimental dots. From here, we have the scaling parameters that we obtain the percolation threshold that is observed that is different depending of the filler that we are using, and also we have the critical index that it shows or tell us which type of mechanism we have in the electron transport. So if we have a critical index higher than 2, it means that our conductive path or electron transport is due to the tunneling effect, meaning that there is no necessity of conductive fillers to be in touch in order to transport the electrons. It's enough to have a distance smaller than 5 nanometers in order to the electrons to jump and form the conductive path. And if we have this critical index at value between 1.6 and 2, what is formed is the so-called electroconductive clusters. And we observe that the polymeric composites based on thermally expanded graphite are at this age between the range of the formation of electroconductive clusters and the tunneling effect. Our hypothesis is that the conductive path of these polymer composites are formed due to both mechanisms, the tunneling effect and the electroconductive clusters. And in order to show that our hypothesis is correct, we also measured the IV curves of the 3 series, before percolation, near percolation, and after percolation threshold. And we observe two different lines. We have the linear response of current to the voltage, meaning that there is no tunneling effect. And when we have a nonlinear shape of the curve, it means that the tunneling mechanism is involved. Furthermore, we fitted these curves near the percolation threshold, and we wanted to see the 2 values that are important, A and B. Here, A is the proportional constant to the frequency of the tunneling, and B is the proportional constant to the tunneling barrier width. These 2 constants are inversely proportional to the other one, meaning that if we have a slower tunneling barrier, a lower tunneling barrier, that means we will have higher frequency because we will have more tunneling in this region. So here we have the data from our series, and we observe that effectively we have this inversely proportionality of the constants. And we observe that with the thermally expanded graphite-based polymer composites, we have the highest frequency of the tunneling and the lower tunneling barrier. As I say, that it's normal because if we are closer, we have more tunneling in this region. So just to conclude, we obtained the polymer composites based on epoxy resin and different carbon fillers by compression molding method. Also, we analyzed the percolation behavior of the polymer composites in terms of electrical conductivity, and it was shown that the type of filler influenced on the percolation parameters. Moreover, in the investigation of current voltage curves of the composites reveals a non-linear behavior, consequence of electron transport by tunneling in the region of the percolation threshold. And of course, this study is under progress, and also we would like to understand better the thermally conductivity of these composites and see how it will behave in the percolation region of the electrical conductivity. And that is all from my part. I would like to thank all my colleagues from the Nanomaterials group, and thank you for your kind attention. And I'm open for questions.
Thank you very much for this very informative presentation. Maybe we have a question in our hall or maybe in Zoom. Any questions, colleagues? So the presentation was full of information and contact you have, and we will move for our next speaker. Thank you very much once again. And our next speaker will be Dr. Yevhen Belyak from Institute of Information Recording NASA of Ukraine with the topic optimization of photoelectric converters. So, Mr. Belyak, the floor is yours.
Hello. My presentation.
One moment.
Can you see my presentation?
Not yet, we are waiting.
It's uploaded.
Now we see, but not in a full screen mode.
Ah, okay. One moment. Now it's okay, yeah?
No.
No. Still not full screen mode, some delay.
Still not. For a full screen mode, you should stop sharing the screen, then put it on a full screen mode, and then start to sharing.
Something wrong with my Zoom. Still no, yeah?
Still not. Can you stop sharing the screen?
There's something wrong with my Zoom. I don't see this button anymore.
Press escape.
Oh, I see, yeah.
And now please start in a full screen mode and only then start sharing.
Is it okay now?
No. Probably you started to share the PPT again, but not the window. Okay, but it's quite good. We have a big screen.
Okay,
so we can
let's see it like that. So I'm from the Institute for Information Recording of National Academy of Science of Ukraine. Today I want you to show our new project. It's quite new, so it wouldn't take long because it's not so much to present. It's optimization of photoelectric converters. Nowadays, miniature cameras, digital cameras is very important. It's in many mobile devices, and I don't mean just smartphones or tablets, but also surveillance cameras, which is very important in our cities. Some cameras in the drones, which proved to be highly inefficient in military intelligence. So there are four main ways to improve its quality. It's optical scheme improvement, which is quite difficult due to the when we need to make it with low mass, low size, low cost, some cameras increase, and some intensive trends like neural networks algorithm to reconstruct bad quality image, and improvement of the photometrics, and this work is just about it. So the main problem is for the cameras of the visual range, multicolor cameras, is spectrum mismatch problem. Photoelectric transducers for photometrics is mostly based on the polycrystallic or monocrystallic scene. So its absorbance spectrum is different from the spectra of the color filters of the triad or tetrad of the photometrics. It's same problems for the photocell, but for the photometrics it's even worse. Because you can see that there are different sensitivity for the three channels. Here I use classic scheme, RGB channels, red, green, blue. So you can see that sensitivity for the red would be better, and the blue channel would be weak link. So not to make a difference in the sensitivity of all three channels, you should calibrate it by the worst one. Our idea of our group was to use photoluminescent coating, which by the Stokes shift transfer radiation of the visual spectrum closer to the peak of absorbance of the photovoltaic transducer. So we have to have three different coatings for the red, green, and blue channel, which is quite a problem. And also we can make other classes of the luminescent dyes for other color schemes, for tetrads like this cyan, yellow, white, and so on. So we decided to use our previous synthesized class of the nanostructured luminophores based on the paraxylene dyes. Basic scheme of the synthesis includes choice of the basic paraxylene luminophore, then the polymer additive, we use PMMA additive or polystyrene additive. Then we use ultraviolet lacquer, usually Rengalux or Rengalux Pro, which makes easier to make a solid dye. And to enhance its parameters, we use nanostructuring of the luminophore. We use white zeolite additive, which characterized it with submicron pores, and thereby it divides dye to the nanoparticles. And while it's not that easy, usually by mixing we got some mix of the bulk material and the nanostructured materials. We also use infrared laser annealing. And then by target indicators, or we may say by target function, while previous procedure parameters could be used as target function parameters. We can find best way to synthesize appropriate material by Stokes shift magnitude, quantum yield of photoluminescence, absorbance spectra, and main peak width. So our first results, first of all, you can see we can got different spectral photoluminescence, same for absorbance for different materials. Then when we use additive, some additive, we can slightly change the spectrum peak. Then by nanostructuring can enhance main photoluminescence peaks. For some dyes, it's added some additional peaks, which is not quite useful here. And then by laser annealing at some regime, it can enhance even furthermore this peak. But then if it would be too much by temperature or time, you can see dye bleaching, its black curve. So you should got the regime of laser annealing by these results. Thereby, we got some first results to enhance photosensitivities of the photometrics and got some better polar balance. There are quite a lot of work to be done. The weak link is blue channel because there should be quite big stocks shift, which we haven't got so far. But if we got a good enough class of luminophores, we could get better photosensitivity and color balance for the photomatrices of visual range by at least persons, as it shows computer simulation so far. Thank you for your attention. Sorry for technical problems. Haven't used Zoom for most time, so sorry.
Thank you very much for highlighting this interesting topic, and maybe we have a question. Do we have any? So thanks once again, no question in chat, and we will move forward. According to our program, the next speaker will be PhD student Yuri Kachurak from the Polytechnic National University, Department of Electronic Engineer, Ukraine, with the topic sensitive liquid crystal composites for optical sensors.
Yes, I'm here.
Okay, please start.
Just a moment, I will show my presentation. So is it visible for now?
Yes, it's okay. Okay, you can start.
Oh, great. So hello, dear colleagues. My name is Yuri. I'm from the Polytechnic National University, Department of Electronics, and today I want to present some results of our team. We investigated liquid crystalline composites as the for sensitive elements of optical sensors. And why we do this? The first goal is to choose the best mixture for future sensor development. We study like three characteristics. It's spectral characteristics of different mixtures, temperature characteristics, and how liquid crystalline mixtures works with some substances which a sensor must react with. Basically, our substance is a mix of pneumatic liquid crystal E7. It's the composite from 4 different cyanobiphenyls and chiral material here is also 4-cyanobiphenyl CB15. We can consider that our mixture is practically homogeneous pneumatic matrix, and it can work. I mean, we don't need to look every component as some others. They pretty the same. It's good metrics for our investigation. So the advantage of choosing components for obtaining sensitive liquid crystal composites for optical sensors is their chemical inertness and the stability of the existence of the mesophase in wide temperature range, likely from 10 to 50 degrees of Celsius. So here the spectral characteristic of mixture components. Here we can, this is the spectral characteristics taken at room temperature, like 21 degrees. As we can see from the characteristic, the materials are characterized by an absorption maximum in the near ultraviolet region, which corresponds to the own absorption peak of the studied liquid crystal substances. In the visible region, it's likely 315, 800, the components are characterized by minimal absorption. Here is the next spectral characteristics. It's the mixtures with our four concentrations. As we can see from figures, the visible parts of spectrum, their absorption at a wavelength that depends on the concentration of CB15 and is obviously related to the formation of the spiral structure of the liquid crystalline molecules. Since the concentration of the optically active impurity was more than 5%, the spiral pitch was determined based on the results of studies of the transmission spectra of the material. The right figure shows the dependency from a maximum absorption peak from the concentration of chiral impurities, B15. The temperature characteristics that are shown on the slide is I'm sorry, temperature measurements were carried in a closed volume at room temperature with partial cooling of the samples with an impurity concentration of 44% of CB15 due to the basic low temperature of the isotropic state transition. The liquid crystal mixture applied to the transparent substrate was gradually heated using warm air. The temperature measurement for 15% mixture could not be carried out due to the low temperature of the isotropic state transition and inability to obtain a sufficient degree of cooling for this measurement. Here is the graphs that shows how our substances works with sensitive sensor substances. I mean, we have the optical gas sensor of acetone or alcohols. And the study of the effect of acetone vapors was carried out according to the next method. The liquid crystalline material applied to the glass substrate at room temperature was located in closed volume in an atmosphere of acetone vapors in the saturated vapor mode. In this way, the dependencies of the chance in the optical absorption maximum of liquid crystalline samples exposed to the vapor of harmful substances were obtained. Consider the process of interaction of a holosteric mixture with acetone. Under the influence of acetone vapors, the pitch of holosteric spiral changed. When the concentration of acetone vapors increase, the critical concentration is reached and the orientation order parameters will decrease to such an extent that the transition to the isotropic phase occurs. After a certain time, acetone evaporates and the reverse phase transition into orientally ordered holosteric phase will occur. As you can see, also the time dependencies here, the acetone works better with substances more quickly, and alcohols more slowly, but we can see that different mixtures, likely here 38% of CB15 and here's 44% of CB15. The mixture with 44% got better time results for with ethanol. It's likely 120 parts per million. And based on these results, from our 4 mixtures, we can choose 2. It's the mixture of 62% E7 and 38% of CB15, and the second one is 56% of E7 and 44% of CB15. And we can conclude that they are the best with their parameters to use them as sensitive element for optical gas sensors. The mixture with 38% CB15 is has better temperature stability, and mixture with 44% of CB15 got a higher sensitivity but a lower temperature of the transition to the isotropic state. And this result can be used for next works which can belong to development of optical gas sensors based on these mixtures. Thank you. That's all.
Thank you very much. Do we have any question? Yes, we have one question, please.
Okay. Dear Mr. Professor, I have questions. I saw you used you provided a measurement and it's pretty close to the phase transition temperature, as for example, in this. Does it had influence on parameters of your liquid crystalline sensors?
We use especially the sensitive element as like it changes parameters as transferred to the isotropic state under the vapors of acetone or alcohols, and it's the main thing how it works. So we need to see the transfer to the isotropic state of these mixtures, and then we can see the for its parameters like the time, how long it was. We can see the concentration of these substances.
I see. Thank you.
Okay.
We have a comment in a chart that E7 and plus CB15 in mixtures have no absorption in visible range. What we see is selective reflection.
It's maybe quite true. Maybe I'm just a little wrong with what I said, but it's true. Andrew is right. Yeah, it's a selective reflection.
So thanks for our chat for this small correction, and thanks once again to Yuri Kachurak for this presentation. And we will go forward to the next speaker. It also will be a PhD student, Vitaly Zadorozhny, from the Kryvyi Rih State Pedagogical University, Ukraine, with the next topic, ab initio study of the piezoelectric effect of the two-dimensional semiconductors of force groups of monochalogenic terts, probably it's German selenium. Okay. Vitaly, can you start? Vitaly, are you here? Okay, probably Mr. Vitaly is not connected yet, and according to the plan we have a coffee break, so I think we can shift the coffee break and start it now, and if Vitaly will connect it later, we will start from his topic or we'll move forward according to our program. So once again, thanks to everybody, and we will start our next session at 16 o'clock on Kyiv time. So, dear colleagues, we can start our next session. And according to the program, the next speaker will be PhD student Denis Samoilenko from the Institute of Physical Chemistry of NASA of Ukraine with the topic plasma catalytic conversion of CO2 over metal oxides catalysis. Please.
Greetings. Can you see my presentation?
Yes, we can see it on a full screen mode. You can start.
So again, greetings, dear colleagues. Nowadays, the increase of anthropogenic carbon dioxide emissions has stimulated the establishment of global goals and local regulation to limit global warming to 2 Celsius degree per year. Reducing greenhouse gas emission, producing energy from renewable sources, and improving energy efficiency are imperative to achieving this goal. The process of carbon dioxide conversion of methane is promising from the point of view of ecological catalysis, as it allows to involve carbon dioxide in the production of syngas and in the future to obtain valuable organic products. A promising method of involving carbon dioxide in production process may be the addition of cold plasma. So what about plasma catalysis? The advantage of this method in comparison with traditional catalysis is the possibility of achieving a synergy of high selectivity of catalyst with a high reactivity and effective plasma energy transfer. In general, the essence of plasma catalysis can be described as a generation of reactive particles in the plasma conditions and their interactions on the surface of the catalyst with the formation of valuable products with high degree of conversion and selectivity under the conditions in which this process will be thermodynamically impossible without plasma. As a result, in a long term, this will lead in a reduction in production costs and make this technology attractive for investments. So on this slide, we can see our plasma catalytic installation and the scheme of it. Research on the plasma catalytic conversion of the carbon dioxide metal mixture was carried out using the installation with a flow reactor equipped with a power source, plasma generator, and oscilloscope. The plasma catalytic reactor is an atmospheric reactor with a dielectric barrier discharge equipped with a high voltage metal electrode with a diameter of 4 mm. Rods tube made this rods and tubes is made with stainless steel, copper, aluminum, titanium, and nickel electrodes were tested. And the catalyst fraction in next discharge was placed in the discharge zone between the high voltage electron and the quartz tube. Some tests within different inner electrode material were carried out. Tested copper electrode was characterized by the highest conductivity among the studied electrodes and highest methane conversion observed. Instead of the highest CO2 conversion was observed by aluminum electrode. However, it is known that the surface of aluminum is always passivated and accordingly covered with aluminum oxide. Thus, the plasma activated particles interacted with on the oxide surface. With the increased decrease in the production of the reactive components, such as CO, methane, and carbon dioxide, the degree of component conversion decreased or increased accordingly. As the proportion of methane in the reaction mixture increases, the yield of the hydrogen and the hydrocarbons in the reaction products increases. With the increase of proportion of carbon dioxide in the reaction mixture, the output of CO increases significantly, while the output of oxygenates does not increase. This may indicate the oxygenates are formed by the interaction of CHX radicals formed during the activation of metallic plasma with CO2 or CO is formed by the the main product of the CO2 activation is CO and oxygen atoms and radicals, which interact with hydrocarbons and hydrogen. By our colleagues in Liverpool, where some studied the possible reaction mechanism of plasma. So which are presented on the slide. The preset of the ethyl acetate, which is a product of the interaction of the acetic acid and ethanol, indicates that the interaction of CHN radicals with CO2 and CO is equally likely. Since the yield of oxygenants also decreased during the transition from the ratio of mixture CO2 to CO4 1:1 to CO4 to CO2 2:1, it can be assumed that the necessary condition for the formation of oxygenates is also the presence of the required amount of carbon dioxide in the reaction mixture. The next stage of our research, we're testing the catalyst inside the plasma catalytic reactor. So the samples were presented between the electrodes in the so-called charge zone. Process of plasma catalytic conversion of CO2 and CH4 mixture at normal was performed at normal temperature and atmospheric pressure. And was precisely performed on such catalysts which you can observe on the slide. Based on the obtained data, it can be concluded that the nature of the catalyst affects the selectivity for products. In particular, catalysts containing metal or semiconductors provides higher yield of CC coupling compounds, such as SN, ethyl acetate, and ethanol. Comparison of data for samples with different acid-basic characteristics also indicates that such parameters affect the selectivity of the plasma catalytic process. Depend on the acid-base characteristic of the catalyst. On the surface, the sample are adsorbed part of the products of the plasma catalytic reaction. Highest conversion rate was achieved with such catalyst as CO on aluminum 2 or 3 sample, respectively 28% conversion by methane and 17% by CO2, with H2 and CO and SN yields respectively 6, 3, and 5%. Such as conclusion, I could say the combination of activation of gas mixture by cold plasma and the interaction of occurred particles on the catalyst, which are placed in the charge zone with optimal catalyst with optimal acid base and redox properties, ensures the transformation of reagents into valuable products of CC coupling. With an increase in the proportion of the catalyst in the discharge zones, the yield of CC coupling products increases with the simultaneous decrease of yield of syngas, which may indicate the coupling of radicals activated in the plasma on the catalyst in the process of plasma catalytic reaction. Thank you for your attention.
Thank you so much for your presentation. Maybe there is a questions in conference hall, maybe in the Zoom. Thank you. We don't have a question, so we move forward to our next speaker. This will be Professor Sergei Kurta. Kurta, are you here?
Yes, I am.
Okay, perfect. Please start your presentation.
Yes, of course. Just a moment, please. Well, you can see my presentation.
Yes, we see your presentation, but not in the full screen. Please stop screen sharing, then start slideshow, and then switch to screen sharing.
Screen sharing. I don't remember your recommendation, and maybe repeat.
Stop screen sharing, then start the slideshow of the.
Stop video or stop screen sharing?
Stop screen sharing. I'll stop it for you. Then
I cannot, but sharing screen and this.
If you want, we could share a presentation for you.
Mr. Professor?
This?
Just a moment. Oh, that is perfect. Yes. Thank you.
It's normal, yes? Okay.
Yeah, perfect. Thank you. You could start.
Okay. I'm very glad to welcome participant of scientific conference, Scientist 10 Conference, Nano 2022. And let me introduce and present our work, decrystallization and stabilization of liquid bee honey during storage. This result we obtain of the department and the chemistry, the Vasil Stefanik Nation University from Ivano-Frankivsk, Ukraine. And this may be so, it's, okay. Let me describe this, my slide. It's this exchange, but I cannot. Alexander. Okay, this papers, our work, the development of new technologies, method, and select special condition and equipment for the breaking down crystallization honey and stabilization liquid honey from the natural crystallization, as well as condition and means of storing honey in liquid state for at least 1 year. Our task to develop of the technology, dissolving the crystallized honey and stabilizing liquid honey, which and the respects correspondent to normal natural honey, with the presentation of liquid aggregate state with a long-term storage of the at least 1 year. And we create some new method and condition for low temperature isothermal accelerating processing of the liquid in crystallization, crystallized honey, and the meet would require the Ukrainian State Technical Service. And we to create, design, and manufacture to the research industrial installation for the low temperature isothermal dissolution of crystallized honey and stabilization, and some packet of the swallow and thermic and special containing for the testing of properties honey during long-term storage at least 1 year. We can know that some very interesting product, the epi product of beekeeping. For example, honeycomb, you can see of our slide, Zabrus, and you can see in two photo, beeswax, and you can see on 3 photo, bee pollen, you can see of 4 photo, and the bee propolis, and the liquid bee honey. Honey is unique product of natural origin, and the value of which is extremely high for a human health. It consists some huge amount, Zabrus, wasp, propolis, bee pollen, and others. Meantime, and acacia honey contains the lot fluid sugar and can remain liquid the sealing honey 1 or 3 years. But other sort honeys extracted from the honeycomb has shelf life only 1 to 6 months, depending on the type and variety mono or polyfloral honeys. On this slide, we can see some type of the honeys, And this describe about how to do crystallization of honey. According to the biological origin, honey is divided into monoflorin, polyflorin, paddy, or mixed. There are 21 species honey product by bees from the nectar and mainly on plant species such as the monoflora acacia, hitten, linden, polyflower contact the floral, the various plants. On this slide, we can see some very interesting honeys about colors. Colors in species and various mono and polyfluoride honey. The great importance of the crystallization honey is the mass fraction is water. At water contain 60 and 20 in honey, crystallization process rapidly. More water than 21, honey remain liquid, transparent, and almost colorless for a long time. For example, acacia, it's time to 6 months. The honey contain more or less primary crystal around which the glucose, great sugar, crystallize. However, the presence and the pollen grain at plant has the stronger effect of the number and size crystallized. This is a slide, you can see some pollen, bee pollen, and you can say some bee to height and legs. Bee pollen and the pollen collecting the honey and size these particles and 8 to 200 microns, which is a glue, bee glue, with a secretion of silvery glands and nectar into the lump on the multicolors granules and the maybe 1 to 3 millimeter. You can see to the figure number 4.2. Colors may be so yellow, purple, depending on the honey smell, and it's very interesting, and the aroma and almost tasty. The composition, the pollen contains 8 to 10 water, 20 or 40 carbohydrate, and 25 and 35 protein, and fat, 5 or 7%. On this slide, we can see the microscope photo. The natural bee honey after 6 months the storage at the normally temperature, before and after low temperature isothermal express treatment with the pollen particle. Figure 5 and 1, the size pollen in the honey before the processing, diameter pollen 50 or 100 micron. But the figure number 5.2, we can see honey bee is transparent after processing, the size of the pollen, diameter, and 10 or 20 microns on the microscope in BC 20. Well, it's normally equipment for the dissolved crystallize. You can see the figure on 6:1. Honey by crystallized thermal method, heating by heat transfer with electric injection or stirring. But for our site, we can use equipment for the dissolving crystallizing honey by low temperature isothermal express heat treatment by special method, the microwave processing. You can see of this slide. Well, on this slide we can see two sort honey. The figure 7.1, we can see crystallized honey without treatment after 12 months of storage. And the figure 7.2, you can see the transparent honey after low temperature isothermal express processing with the use of special equipment after 12 months storage. And you can see that right honey is liquid, but left honey is solid. On this slide, we can see the microphotos, the crystal, glucose and the sucrose of natural bee honey after 6 months storage, and the figure 4.1. And the other and the 2 for crystal honey diameter has a diameter 500 on the 1000 micron. On the figure number 4.2, we can see honey after low temperature, 20 degree Celsius isothermal acceleration processing in the microwave, 60 seconds, and storage for the 6 months. And the diameter crystal is the 1-200 microns. Well, we can describe it and investigate for other obtains honey. For example, analysis diastase number and content oxymethylfurfural. And during the dissolution of crystallized honey, be heating by heating transfer and isothermal low temperature express heating. And we can see that depends of the diastase number, honey, it's got it on the temperature and the heating time during heat the transfer. Figure number 2 depends of the hydroxymethylfurfural. Well, for us, very interesting for the what the kind about the honey after the express thermal treatment, and we can see infrared spectral honey. The red unprocessed natural honey, and blue is the honey after low temperature processing. And we can see that infrared spectra not different some. And for us, it's very important to distribution of mass distribution particle of natural unprocessed honey, average the particle diameter of 12 nanometers. And for the honey after the heat treatment, diameter particle, average diameter particle is 6,000 nanometers. And you can see of this slide. Well, and we have some investigate another properties of the honey, the chemical consumption of oxygen in the laboratory samples of different special honey. You can see on the left figure, and the biological consumption of oxygen in laboratory sample of different type of honey. And we can see that after a treatment, in the heat treatment, this biological consumption and the chemical consumption oxygen is not so decreased. Well, For us, it's very interesting to the content, the elements according to the result of X-ray fluorescence spectroscopy in honey. And of the left figure, number 13, we can see some content, the elements honey after and before and after treatment. And the figure number 14, you can see the content that dissolve oxygen in aqueous solution of different type of honey. And we can see this very interesting result for this. Well, and to our aim for us is very interesting to obtain liquid honey, which to vary storage and at least the 1 year. And this photo, you can see the mini package for the honey, 30, 40, 50, and 100 milliliter to 500 milliliter, in which we can see dissolve the crystallized solid honey in the accelerating isothermal way and stabilized and liquid transparent honey, its properties and the physical state on for a 1 year storage under condition. Well, and this is, can you see, patent for the prevented having gum, medium-neck honeycomb, prophylactic having gum, based on the dissolving crystallized honey, wax, and big glue. Well, and this slide, we can see the laboratory samples, the prophylactic having gum, medium-neck honeycomb, made from the dissolving crystallized honey, wax, and big glue. We manufacture the prototype laboratory sample for the having gum in the form of sweets. We recommended the having gum at 10 or 15 minutes, 3 times every day after meals. And the honeycomb, this prophylactic having gum from the periodontal diseases. For example, the gingivitis, periodontitis, and the periodont. And on this slide, we can see the document about the laboratory, clinical laboratory investigate of our prophylactic having gum with the dissolved crystallized honey. And conclusion, we can, the method of the industrial technology for the low temperature isothermal acceleration processing dissolving crystallized honey. And it's main, we prepare on the dissolved crystallized made, the having gum from for the under the periodontosa and other deletions. This is a literature and reference of our work. This is the website of our works. We can see and we can interested. And this is my team, consisting of Olga Hatsevich, the PhD Department of Chemistry, the PhD Sofia Fedorchenko from the Department of Chemistry, Petrograd National University, and the Bachelor Magomed Tagir. This is all. I wait your questions.
Thank you very much. And do we have any question in chat maybe? Yes, we have one question in our hall, please.
Okay.
One moment.
I listen.
I have one question. How are you going to extrapolate your result for different types of honeys that are composed from different types of pollen? So basically, you have honey that is composed from a random mix of pollen. How are you going to extrapolate your result to different types of different honey?
You must have that the natural honey consists some very particle pollen.
Yes.
And other, for example, this particle is not so very small. It's so very big, and the process crystallization to obtain of this particle, the pollen. But it's very difficult to obtain some liquid honey without pollen.
Okay, thank you for your answer.
Thanks once again, and according to the program we should move forward. So, Professor Kurta, thank you very much. And the next
Thank you very much, Paul, for all.
The next speaker will be Dr. Oksana Koplak from the Politecnico di Milano, Italy. And the topic will be slowed magnetic relaxation in the Earth 3+ single ion magnet in the absence of external magnetic fields. So, Dr. Oksana, can you start your presentation? We already see the first slide, but cannot hear you.
Dr. Koplak, you're muted. Please turn on your microphone. У нее замоченный микрофон.
Okay, can you hear me?
Now we can hear, but the sound is very weak. You can probably move.
Okay, and now?
Now it's better, and we see your presentation. Please start.
Okay, thank you very much. My presentation not so sweet as previous one. It's very interesting to hear a presentation on the scientific conference on the honey. So, but first of all, I would like to thank the organizing committee. You have been doing great and important work for many years. And my congratulations on anniversary of the conference. I wish you all success and all the best. Okay, I have been participating in this conference for several years, and today I will talk about slow magnetic relaxation in molecular magnets. So, single molecular magnets or single ion magnets are currently attracting a lot of interest due to their potential application in spintronics and quantum information processing. You know, now it's one of the main topics in scientific journal, some big project, etc. Typical molecular magnets are complexes that involve a magnetic ion incorporated in organic structure, chemically designed to satisfy desirable symmetry of the ligand field. These complexes form molecular crystal lattices where solvent molecules separate magnetic complexes for a long distance. It can be from 10 to 30 angstroms. Separation of spin provides their magnetic isolation from each other. More or less strong coupling between an ionic spin and organic environment is provided due to the spin orbital interaction within the complexes. And the chemical design is focusing on this one. Of course, there are a lot of some problems. First of all, it's a chemical stability. Another one, it's a possibility of multiply switching of the magnetic state of magnets, and etc. And one of the more important, it's observation of slow magnetic relaxation in molecular magnets just in the presence of the external magnetic field. This such of compound names field-induced molecular magnets. So what it means? It means that you can see magnetic relaxation just in the presence of magnetic field. It can be clear at the temperature dependencies or the frequency dependencies of magnetic susceptibility, real or imaginary part. And in this case, you need to use the external magnetic field, and time to time the magnitude of this field can be reached to a few kilo-oersted. It's not compatible with the strategy of the design of the low-energy local memory elements. So, in this case, what we can do? We propose one of the nice idea to change the magnetic field. Instead of the field generated by external electromagnet, one use a controllable internal magnetic field. So, what it means? It means that we can use a magnetic field from permanent magnet, such as magnetic microparticles. You know that rare earth transition metal alloys demonstrate very nice magnetic properties at room temperature also. What it means, it's a high value of residual magnetization and high value of coercive field. The hysteresis loop more or less squared can be at room temperature. We used this type of alloys that consist of praseodymium, dysprosium, iron, cobalt, bore compound elements, some microparticles with help of gas atomization was produced. In gas atomization, the feedstock element or metal or alloys, in our case it was alloys, is melted in a furnace, usually in a vacuum. We used a very high vacuum to be sure that we haven't no any impurities, no any oxygen additional phase, because it's so dangerous for creation of hard magnetic phase. So the furnace is positioned above the atomization chamber for direct material discharge into the atomizer. In gas atomization, the stream of liquid metal is broken by a high velocity gas flow. And finally, we will have some balls, microparticles that was absolutely spherical, with very nice surface, with very low roughness. You can see these images that was obtained in electron microscope. This is like ball, very beautiful one. The size distribution can be different ones, can start from 5 to 2 microns till to 200 microns, but we can distinguish, we can separate the size which you need, what we need. So, we did some XRD analysis of these microparticles, and you can see the dependencies that correspond crystal phase and amount of the rare earth hard 241 phase more than 92%. It means that it's a really hard magnet. It works at room temperature and demonstrate the high value of residual magnetization, as you can see from the hysteresis loop. So we use these microparticles for the composite materials that consist of mix these microparticles and molecular magnets. And we hoped that this residual field was enough for induce a slow magnetic relaxation. On these dependencies that you can see on the right side of the slides, one can see that in the zero external magnetic field, no any peaks on the frequency dependencies of magnetic susceptibility wasn't observed. This peak possible to observe just in the presence of external magnetic field. It's really field-induced molecular magnets. And the magnitude of the field should be more than 3,000 oersted. It's too much, yes. But when we add the magnetic microparticles in these composite materials, we can see these peaks without any external magnetic field. It's a bottom picture that you can see it there. So this result was already published in this journal. And we continue our investigation, and the big question, so can the ability to adjust the residual magnetization of macroparticles be an external field as universal? And can be used to control spin relaxation in nanocomplexes of various origin. That was done, it was for molecular magnets with magnetic ion from transition metal, cobalt 2+. But if we do the same for rare earth ion, it can be reproduced or not. It's a big question because it's a rare earth metal, it's a lanthanide family that have a bigger one, magnetic moment, bigger magnetic crystalline anisotropy, etc. So, and we it was aim of our work. We used these molecular magnets with erbium, and you can see this formula, and ground state you can see so. As I said, it's compounds with high angular moment and significant magnetic anisotropy that provides slowing of the magnetic relaxation in the presence of the equatorial donor ligands. So, and additional advantages of the compounds that have a large barrier of magnetic anisotropy, and additional one that is a compound demonstrate nice optical properties. So it means that we can combine magnetic and optical properties for additional advantages for application. So, okay, and we use this compound. Okay, and if this idea works, it means that we will find some very simple way for prolongate the relaxation time in this compound. Oh, I'm sorry. Maybe not too nice to hear me. Okay, and we attest. We did some attestation of our complexes that was performed by scanning electron microscope, energy dispersive microanalysis, etc. Optical transmission electron microscope, and you can see that it consists. Sorry, maybe it's not good to hear me. Yeah.
It's okay. It's okay.
It's okay? It's okay? Sorry for this one. Okay, I will continue. And you can see the powder molecular magnets covered the microparticles, and erbium was distributed everywhere. And erbium was distributed everywhere, including the space in between microparticles. No any additional impurities wasn't observed. It means just two compound can be analyzed. So first of all, we measured local magnetization by IFM magnetic force microscope, and you can see two images that correspond profile of surface and magnetic structure. We used magnetic cantilever. It's a two-step recording. First step, you can measure the roughness, and the next step, you can measure the magnetic gradient of magnetic force. And on this slide, you can see, on this second picture, you can see two magnetic singularities that demonstrate residual dipole magnetization of the microparticles, magnetized in the same direction. Black and white, it means direction of magnetization up and down. So, okay, and we hope that it will be enough, this magnitude, this stray field will be enough for switching or re-switching our molecular magnets. And we measured set of dependencies of magnetic susceptibility, real and imaginary part, okay. And you can see here that first, it's unbelievable. All words can start something. Sorry for this. Okay. Up. This frequency dependencies that correspond for pure sample that compacted erbium pellet free of ferromagnetic magnetic ferromagnetic microparticles. It's just molecular magnets. And the picture bottom, it's a sample that was composite. It's a mix of microparticles with molecular magnets. This dependencies was recorded at external magnetic field at 1050 Ørsted in temperature range from 2 to 4 K. And with increasing the temperature, this peak shifted for both samples. But I repeat that it was recorded at presence of external magnetic field. In zero DC magnetic field, no any peaks wasn't observed, or no any dependencies on the temperature dependencies or field dependencies of the magnetic susceptibility. So no any magnetic relaxation in zero external magnetic field wasn't observed. Sorry, I repeat again. But when we magnetized our microparticles and measured again, we can see very beautiful peaks on the frequency dependencies of the real and imaginary part of magnetic susceptibility. It means that we switch some mechanism for producing magnetic relaxation in a very simple way, just when we magnetized our microparticles in zero external magnetic field. So we combine all dependencies and plot some call diagrams. It's some very famous formalism that you plotted real part versus imaginary part, and you can see this call. Call is a family name, but when you analyze this diagram, you can extract directly the relaxation time. And we did it for two types of samples, for pure molecular magnets and for these composite materials. And you can see that these two curves, different one for sample 2, it's lower. It means that this difference reaches at least one order of value at 2K, and we can conclude that ferromagnetic environment decrease of relaxation value of relaxation time. Okay, and high temperature, high 4K, it's not so high, of course, but it's a helium temperature. This compound can work just at this temperature. And the 4K difference between curve 1 and curve 2 disappears. Because the field-independent Raman and Auerbach magnetic relaxation becomes dominating. I should say that in this compound, 3 types of relaxation mechanism can be as driver. It's a Raman, Auerbach, and tunneling mechanism. What is the reason, what is the origin of our effect? We try to answer by this plot. We plot the field dependencies of relaxation time and deviation of remanence magnetization. And both of these curves.
No question yet, and we can't wait. So we should move forward. Thank you very much, Oksana. And the next speaker will be Dr. Alexandra Bazan-Wozniak from the Adam Mickiewicz University in Poznan, Faculty of Chemistry, Poland. And her topic will be adsorption of cationic dye onto biocarbons, kinetic and thermodynamic study.
Yes, can you hear me?
Yes.
Okay, so I screen my, okay. Do you see my presentation?
Yes, you can start.
Okay, thank you. So good afternoon, ladies and gentlemen.
My title of my research is Adsorption of cationic dye onto biocarbons, kinetics and thermodynamic study. We know that every day huge of amounts toxic gas and industrial waste are released to the natural environment, and volatile compounds such as nitrogen and sulfur belong to the pollutants most often emitted to the atmospheric air, and it is have answerable effects to human health. On the other hand, textile, cosmetics industries and generate large amounts of dye and metal ions and polluting ground of surface waters. And we know that one of the most effective methods for the removal of these pollutants is adsorption, and one of the most effective adsorbents are activated carbons. The precursor of activated carbons can be any material contain carbon in organic combination. And a very promising and interesting precursor can be residues after supercritical extraction of plants and their elements. According to the literature data, we know that extraction with liquid in a supercritical state is of growing industrial significance. So the amount of the waste from this process is expected to increase with time. We know that production of activated carbons based on two methods, physical activation and chemical activation. The process of physical activation based on two mechanisms, carbonization and activation. In carbonization, our precursor was thermal, the composition with nitrogen, usually gas atmosphere. And next, the carbonizate products was be an oxidizing agent, usually carbon dioxide. Another method is chemical activation, and in this method we impregnation our precursor with active agent and subject him to thermal treatment in a neutral gas atmosphere. Activated carbon can be obtained in conventional method or conventional method of microwave oven. And in addition to the starting material method and method of heating of obtained activated carbons, their sorption properties are also affected by surface chemistry, crystal structure, and porous structure and presence of active places. And the aim of the study was to obtain a series of low-cost biocarbons by physical and chemical activation from residues after supercritical extraction Roseberry set, and next eliminate rhodamine B from water solution. And the precursor was carbonized under a nitrogen atmosphere at 500 Celsius degrees, and the process was carried out in microwave oven and conventional oven, and carbonization products were activated with carbon dioxide at 700 Celsius degrees, and I using different activation times. Second method to obtain biocarbons is chemical activation. The activation agent was potassium carbonate, and the weight ratio precursor to activator was 1:2. And the impregnated temperature was 700 Celsius degrees, and 4 times 30 minutes to microwave oven and 45 minutes in a conventional method. And the obtained activated biocarbons were assigned the symbol shown on the slide.
Elemental analyzers and textural parameters was carried out for all biocarbons. The acid-base properties of the obtained adsorbents were determined using Boehm titration, and for the obtained biocarbons, adsorbents were tested from the liquid phase using rhodamine B as an example. The next slide shows the elemental composition of the samples obtained as follows from a comparison of results. The activation methods and the method of heating have little impact on the elemental composition. The elemental carbon connect range 80 to 93% by weight. Hydrogen is 2 or 3% by weight, and the PAM sample obtained by physical activation in microwave oven has the highest oxygen content of about 13% by weight. The next slide shows the textural parameters of biocarbons obtained by physical and chemical activation of the precursor. Specific surface area, total pore volume, microwave volume, and average pore diameter was obtained, and the surface area of the biocarbons varied from 468 to 1078 square meter per gram, and the larger surface area and pore volume has sample CAC prepared by chemical activation on a conventional heating, and the physical activation leads to sample of poorer surface area than samples prepared by chemical activation. And moreover, conventional heating was found to give a sample of development surface area than a sample obtained by microwave oven. And the highest contribution of micropore volume had sample obtained by chemical activation of the precursor. Next slide showed acidic and basic groups for the biocarbons obtained by Boehm titration, and they analyzed reveals that the chemistry of the biocarbons depends first of all method of activated of biocarbons obtained, and next mode of heating. And sample PAM and PAC prepared by physical activation showed basic character of the surface, and the sample activation with carbon dioxide with potassium carbonate generation acidic groups. In the next slide, stage of the study, I evaluated the adsorbents obtained by physical and chemical activation of the precursor for their removal to rhodamine B as an example, and I'll calculate the amount of the diadsorbent according to the formula present in the slide. And as a part of the study, I analyzed the effect of process temperature and time of contact of the dye solution with the biocarbons. All biocarbons obtained were tested, and sorption capacities was in the range from 80 to 180 milligram per gram. The efficiency of sorption of dye was observed depend first of all method obtained and next mode of heating, and the highest sorption capacity has sample CSC prepared by chemical activation in conventional with a conventional method. Sorry. And the sorption capacity for sample obtained by chemical activation are
are higher than physical activation. And the effect of contact time of adsorbent and adsorber I was also characterized. And as we can see in the first 40 minutes of starting, the rhodamine B was very fast adsorbent of the biocarbons. It means that a large of number of active centers of the surface we had, and as follow from 300 to 350 minutes, we have the adsorption equilibrium equilibrium. So we does it mean that we don't have active centers in our solution, and so the sorption capacity does not increase. The kinetics of rhodamine B adsorption on the surface of biocarbons studied was with pseudo first order and pseudo second order kinetic models, and as we can see, the determination coefficient was higher for pseudo second order model. The next slide show the values for Langmuir and Friendlich model, as we can see that Langmuir model is better for biocarbons than Friendlich model. And in the next slide, the effect of temperature of the sorption capacity of the biocarbons was investigated, and the study showed that the dye removal efficiency increased with increasing temperature, and the great effect of temperature we can see to sample CAN obtained by chemical activation in microwave oven. And in contrast, the small gross sorption capacity was to sample PAM. And the next slide, we have figures to sorption capacity of my best biocarbon sample CAC and the other adsorbents in liter data, and we know that we see that sorption capacity for sample CAC is very promising to other adsorbents. Only the highest sorption capacity had towards rhodamine B showed magnetic mesoporous carbon materials, but of course these samples obtained is not cheaper than my biocarbons. And as we can see to my presentation, the surface area and degree of pore structure depend of method of activation and more of heating. The physical activation favors the basic of groups, and chemical activation of the precursor lead to prevalent formation of acidic groups. The efficiency of rhodamine B depends on method of activation and mode of heating, and time of contact of the adsorbent, and of course temperature of the reaction. And the best effective adsorbent was sample CAC, chemical activation conventional method, and the amount of adsorbent rhodamine B was also found to increase with increasing temperature. And we have this mechanism was described by Langmuir model and pseudo second order kinetic model. And thank you for your attention.
Thank you very much. Probably questions?
Yes,
yes, one question, please.
Can I?
Yes, yes.
Okay, I have very short, maybe technical question. Can you explain how you measured surface area? Which the method you used? Maybe it was method BET, so it's very important information for your sample and for your conclusion. But first of all, please describe the technical step how you measure it, because a lot of errors can be find during this measurement. Thank you.
Yes, I described my surface area from BOEM method, BET method, of course.
Yes, it's a BET method. Yeah. Did you use?
Yes, BET method.
But at which temperature? It was the same condition or not? Maybe you find some additional non-reproducible curves. No, it's just everything was perfect.
Sorry, can you repeat?
Maybe I can ask you later. So, or I just would like to know the technical experiment that was did because.
We characterized by low temperature nitrogen atmosphere adsorption-desorption isotopes.
Okay. Thank you again.
Okay, thank you for this conversation, and we will move forward. Thanks once again to Alexandra Wozniak. And let's move forward. Our next speaker will be Darina Mruga. Can you hear us, Darina? Darina? Unfortunately not yet. Possibly she will come later, and then we will give her floor. So let's move forward through the program. Evgenia Nesterenko. Miss Evgenia. Or Dr. Petro Litvin. Understandable that the last speaker can be not here because his speech should be at 17:30, and I think we will have a 10 or maybe 15 minutes break, and if our participants will came, we will continue. If not, that will be the end of this day. So after 10-15 minutes we will inform will we meet already tomorrow or will we continue today. Thank you, and 10 minutes break. So as nobody connected yet, and the last speech should be at 17:30, and the reporter is not connected, I think that we should not wait anymore. If this speaker will contact us, we will give them time tomorrow. And for today, we can close our second plenary day, and we'll be happy to see and hear you tomorrow at 9 o'clock.
And today at the beer.